Subscribe to the channel so you don't miss out on any of these videos. Space is full of mysteries, but there's one that defies our understanding of reality itself. Imagine a place where even the fabric of space-time gets twisted, where the laws of physics take a strange turn, and where energy might be extracted from the most destructive forces in the universe. This isn't science fiction. This is the ergosphere of a rotating black hole, a region where space is literally dragged by the spin of the black hole, creating effects so bizarre they border on the impossible. What's really happening in this zone? Could this strange phenomenon hold the key to unlocking boundless energy? And what does it reveal about the very nature of our universe? Let's dive in. The story of the ergosphere begins with the idea of rotation. We're all familiar with objects spinning, planets rotate, stars rotate, and even galaxies rotate. But when a black hole spins, something extraordinary happens. To understand why, you first need to picture the immense gravitational pull of a black hole. It's so strong that nothing, not even light, can escape from the event horizon, the boundary marking the point of no return. But in a rotating black hole, or curved black hole, the story becomes even stranger. When a black hole spins, it doesn't just sit there, minding its own business. It drags the very fabric of spacetime around it in a process called frame dragging. This effect, predicted by Einstein's general theory of relativity, is like what happens when you stir a spoon in honey. The honey near the spoon starts to swirl, and the closer it is to the spoon, the faster it moves. In the case of a black hole, the spoon is its immense gravitational field, and the honey is spacetime itself. The ergosphere is the region outside the event horizon where this frame dragging becomes extreme. Here, spacetime is twisted so violently that nothing can remain stationary relative to the distant stars. Even if you're just sitting there, minding your own business, you'll be dragged along with spacetime, forced to rotate around the black hole. This might sound harmless, but it has profound implications for our understanding of energy, motion, and even the survival of matter. The boundary of the ergosphere is defined by a point where spacetime is dragged so fast that anything within it must move faster than the speed of light to remain stationary, a physical impossibility. As a result, objects within the ergosphere are compelled to move in the direction of the black hole's spin. This might sound like a trap, but it's actually an opportunity, especially when it comes to energy extraction. One of the most mind-bending aspects of the ergosphere is the possibility of extracting energy from it. This idea was first proposed by physicist Roger Penrose in the 1970s, and it's called the Penrose process. The concept works like this. Imagine throwing an object into the ergosphere. Because of the unique properties of spacetime in this region, the object can split into two. One part falls into the black hole, while the other escapes, carrying away more energy than the original object had. Essentially, the black hole's rotational energy is tapped, slowing it down slightly while releasing usable energy. It's like stealing energy from a cosmic whirlpool. The implications of this are staggering. If we could harness the Penrose process, we'd have access to a near-limitless energy source, theoretically more efficient than any method currently known. But there's a catch. The technical challenges of extracting energy from a black hole are immense. For one, you'd have to venture dangerously close to the event horizon, risking being torn apart by the intense gravitational forces. And even if we could overcome these obstacles, we'd still need to understand how to capture and utilize the energy efficiently. Beyond its practical applications, the ergosphere raises profound questions about the nature of the universe. For example, the extreme conditions in this region challenge our understanding of physics. What happens to matter and energy when spacetime itself is distorted? How do particles behave in such an environment? And could the strange properties of the ergosphere provide clues about the fundamental structure of reality? Another fascinating aspect of the ergosphere is its potential role in astrophysical phenomena. Some scientists believe that the enormous energy released in this region could power the jets of plasma seen shooting out from the poles of certain black holes at nearly the speed of light. These jets, which can stretch across millions of light years, are among the most powerful and mysterious phenomena in the universe. Could the ergosphere be the engine driving these cosmic outbursts? The ergosphere also pushes the boundaries of what we consider possible in terms of time and space. The twisted spacetime within this region creates pathways that might allow particles to follow trajectories that defy our usual understanding of cause and effect. Some theories even suggest that the ergosphere could be a gateway to other parts of the universe or even other universes altogether, although this remains highly speculative. And then there's the philosophical side of things. The ergosphere forces us to confront the nature of reality itself. What does it mean when space and time, the very framework of our existence, can be warped and twisted to such an extreme? How do these phenomena fit into the broader tapestry of the universe? And what does it tell us about our place in the cosmos? As we delve deeper into the mysteries of the ergosphere, it's clear that this isn't just a region of space. It's a window into the most extreme forces of nature, a laboratory for testing the limits of physics, and perhaps even a stepping stone to understanding the universe on a deeper level. From the possibility of energy extraction to the potential for groundbreaking discoveries, the ergosphere is a reminder of just how much we have yet to learn, and just how strange and wondrous our universe truly is. The ergosphere isn't just a cosmic curiosity, it's a challenge to our understanding of physics and a realm where theories can be tested in ways impossible to replicate elsewhere. For one, the interplay of immense gravity, extreme rotation, and space-time distortion provides the perfect conditions for probing general relativity. Einstein's equations predict the bizarre effects we see in the ergosphere, but observing these effects in action could solidify, or challenge, our theoretical frameworks. One of the key phenomena associated with the ergosphere is frame dragging, and its implications stretch far beyond just spinning black holes. Frame dragging is a consequence of massive objects rotating, and though it's most extreme near a Kerr black hole, it also occurs on smaller scales. Even Earth exhibits a faint frame dragging effect, known as the lens stirring effect, where the planet's rotation slightly warps spacetime around it. Satellites in orbit have measured this effect with precision, validating Einstein's predictions. However, near a rotating black hole, this effect becomes so pronounced that it governs everything within the ergosphere, transforming the region into a cosmic dance floor where particles, energy, and even light must follow the spin of spacetime. This forced motion introduces a concept physicists call superliminal rotation, though it's not what it seems. Within the ergosphere, objects are compelled to rotate with spacetime. This doesn't mean they move faster than light. Instead, it means that spacetime itself is being dragged around so quickly that no stationary position is possible relative to a distant observer. The practical result? Any spacecraft, probe, or particle entering the ergosphere would find itself swept up in the black hole's spin, creating extraordinary trajectories and interactions. Now, let's revisit the Penrose process, as it lies at the heart of the ergosphere's energy dynamics. Imagine a spaceship venturing into this twisted region of spacetime. If the ship released a payload with carefully calculated speed and direction, the payload could split into two parts. One fragment would be consumed by the black hole, plunging past the event horizon, while the other would escape with more energy than the original payload contained. The math behind this is astonishing. The escaping fragment could gain up to 29% of the black hole's rotational energy. This is effectively a cosmic profit, a net gain in energy achieved through exploiting the strange physics of the ergosphere. While it sounds like science fiction, the Penrose process is firmly rooted in established physics. In fact, this energy extraction mechanism has inspired scientists and engineers to consider its applications, albeit hypothetically for now. Could we one day build spacecraft capable of utilizing black hole ergospheres as energy sources? What would this mean for humanity's energy challenges? The potential is tantalizing, but the technical hurdles are equally staggering. For one, entering the ergosphere safely would require unimaginable precision. The gravitational forces near a black hole are so intense that even the slightest miscalculation could spell doom for any object, or person, approaching it. Additionally, the energy extraction process would need to be perfectly coordinated, as the chaotic environment of the ergosphere leaves little room for error. On top of that, the energy gained would need to be transported and converted into a usable form, a challenge that remains firmly in the realm of theory. But the ergosphere isn't just about energy extraction, it also plays a role in some of the most extreme astrophysical phenomena we observe. Take, for instance, the relativistic jets emitted by active galactic nuclei, where supermassive black holes reside at the centers of galaxies. These jets, which can extend millions of light-years into space, are among the most powerful events in the universe. While the exact mechanisms driving these jets are still debated, many scientists believe that the ergosphere is a key player. The intense frame dragging and energy dynamics within this region may funnel matter and energy into highly collimated streams, launching them outward at near-light speeds. And then there's the potential connection between the ergosphere and exotic matter. Some theoretical models suggest that the extreme conditions within the ergosphere could give rise to states of matter or energy that don't exist elsewhere in the universe. These could include negative energy states, which are crucial for the Penrose process, but also raise intriguing questions about their broader implications. Could such states of matter be harnessed for advanced technologies? Could they help us understand the mysterious dark energy driving the expansion of the universe? The answers remain elusive, but the questions are enough to fuel entire fields of research. Let's not forget the implications for time and space itself. The twisted spacetime within the ergosphere creates conditions where time slows down relative to distant observers, an effect known as gravitational time dilation. This effect, predicted by general relativity, means that an object near the ergosphere would experience time differently from an observer far away. If a spacecraft were to orbit within the ergosphere, its crew might experience seconds while years pass for observers on Earth. This distortion of time opens up fascinating possibilities for studying the universe and even exploring the concept of time travel, though such ideas remain speculative for now. Furthermore, the ergosphere challenges our understanding of causality, the relationship between cause and effect. In this region, the warping of spacetime is so extreme that particles and light can follow paths that appear to loop back on themselves. This raises questions about whether the ergosphere could allow for closed time-like curves, or paths in spacetime that might permit a kind of time travel. While such scenarios are highly theoretical, they provide a glimpse into the profound mysteries that lie within the ergosphere. The ergosphere of a rotating black hole is not just a scientific curiosity, it's a gateway to some of the most fundamental questions about the universe. From the possibility of extracting energy to the exploration of spacetime's most extreme conditions, the ergosphere offers a glimpse into the boundaries of human knowledge, and beyond. It's a reminder that the universe is far stranger and more wondrous than we can imagine, and that our journey to understand it is only just beginning. The ergosphere is also a laboratory for testing the limits of physics. Consider the challenges it presents to our understanding of quantum mechanics, a field that governs the behavior of the smallest particles in the universe. While general relativity describes the ergosphere's large-scale dynamics, the quantum realm introduces another layer of complexity. For example, what happens to virtual particles, pairs of particles that spontaneously pop into and out of existence, when they interact with the warped spacetime near a black hole? Some scientists speculate that these interactions could shed light on the elusive theory of quantum gravity, the long-sought unification of general relativity and quantum mechanics. One area where this interplay becomes critical is in understanding Hawking radiation, the theoretical process through which black holes slowly lose mass over time. Near the ergosphere, the conditions for particle-antiparticle pair production are extreme. One of these particles could be trapped and consumed by the black hole, while the other escapes into space, effectively stealing energy from the black hole's mass. While this process typically occurs closer to the event horizon, the ergosphere's unique environment might amplify these interactions, providing new avenues for studying black hole evaporation and entropy. Entropy itself is a fascinating topic in the context of black holes and the ergosphere. Black holes are governed by the laws of thermodynamics, just like any other physical system. The second law of thermodynamics, which states that entropy must always increase, is particularly intriguing when applied to black holes. The area of a black hole's event horizon is directly proportional to its entropy, and energy extraction via the Penrose process could, in theory, affect this relationship. Could the ergosphere allow for localized decreases in entropy, challenging our understanding of the arrow of time? Or would the laws of thermodynamics hold firm, as they always seem to do? These questions remain unanswered, but they highlight the ergosphere's potential to test our most fundamental scientific principles. Astrophysical observations are critical for studying these phenomena. Advanced telescopes, such as the Event Horizon Telescope, EHT, have already provided us with the first-ever image of a black hole's shadow, giving us a glimpse into the dynamics near the event horizon. However, capturing the ergosphere's effects in detail requires even more precise instruments. Future missions may leverage gravitational wave detectors to analyze the ripples in spacetime caused by interactions near rotating black holes. These waves, which are essentially cosmic echoes, could carry information about the ergosphere's structure and the extreme processes occurring within it. Additionally, the ergosphere's role in high-energy astrophysical events cannot be overstated. Gamma-ray bursts, some of the most powerful explosions in the universe, might be linked to energy extraction mechanisms in the ergospheres of rapidly spinning black holes. Similarly, ultra-high-energy cosmic rays, which bombard Earth from distant galaxies, could originate from interactions within these regions. By studying the ergosphere, scientists hope to trace these phenomena back to their cosmic origins, piecing together the story of how the universe generates and distributes its immense energy. The ergosphere also raises profound philosophical questions. For example, if spacetime can be so thoroughly twisted and distorted, what does this say about the fabric of reality itself? Is spacetime a flexible, malleable medium that responds to the presence of mass and energy, or is it something even more abstract and fundamental? And if the ergosphere allows for phenomena like energy extraction and potential time loops, what does this mean for the ultimate nature of cause and effect? These questions push the boundaries of not just physics, but also metaphysics, as scientists and philosophers alike grapple with the implications of such extreme environments. The concept of the ergosphere even finds its way into speculative fiction and futurism. Writers and thinkers have imagined civilizations advanced enough to harness the energy of black holes, building massive structures, like Dyson spheres, around them to capture their output. Could the ergosphere be humanity's key to unlocking such advanced technologies? While these ideas remain firmly in the realm of speculation, they inspire us to think about the possibilities that lie ahead. The ergosphere is also a reminder of the interconnectedness of the universe. The processes occurring in these extreme regions have ripple effects that influence galaxies, star formation, and even the distribution of matter and energy across cosmic scales. By studying the ergosphere, we're not just learning about black holes, we're uncovering the mechanisms that shape the universe itself. Moreover, the ergosphere challenges us to consider the limits of human exploration. Could we ever venture close enough to a rotating black hole to study its ergosphere directly? If so, what technologies would we need to survive the intense gravitational forces and radiation? While these questions remain speculative, they highlight the ergosphere's potential to drive innovation in space travel, energy generation, and materials science. As our understanding of the ergosphere deepens, it's likely that new mysteries will emerge, each one more intriguing than the last. After all, the universe has a way of surprising us, revealing complexities and wonders that defy our expectations. The ergosphere of a rotating black hole is a testament to this truth, a region where the familiar rules of physics are bent, stretched, and sometimes broken, reminding us of the boundless potential for discovery. The mysteries of the ergosphere extend into realms that may redefine what we consider technologically and scientifically possible. One of the most compelling ideas is that of extreme energy harvesting. The Penrose process is a theoretical framework, but it tantalizes us with the prospect of extracting vast amounts of energy from black holes. If civilizations in the distant future, or even advanced extraterrestrial beings, could tap into this energy source, the implications would be staggering. Imagine a civilization capable of constructing structures to safely approach and utilize the energy of a rotating black hole. Such structures would have to withstand the immense tidal forces and relativistic effects near the ergosphere. To achieve this, they might use materials far beyond anything we can currently produce, perhaps derived from exotic particles or engineered through quantum manipulation. Harnessing the energy of the ergosphere could lead to breakthroughs in power generation, enabling interstellar travel and perhaps even circumventing the constraints of light-speed travel. One theoretical concept closely tied to this is the black hole battery. This idea involves using the rotational energy of a black hole as a massive, long-term energy reserve. A sufficiently advanced civilization could send matter into the ergosphere, carefully orchestrating its trajectory to maximize the energy extracted. This harvested energy could be used to power spacecraft, entire planets, or even vast interstellar habitats. While the mechanics of such an operation remain purely hypothetical, the ergosphere's potential as a limitless energy source continues to captivate scientists and futurists alike. The ergosphere's unique properties also open the door to experimental physics at scales and conditions impossible to achieve on Earth. For example, the intense gravitational fields within the ergosphere could allow scientists to study quantum field theory in curved spacetime. This might help resolve some of the inconsistencies between general relativity and quantum mechanics, particularly in how they handle the concept of energy and information. Speaking of information, black holes have long been associated with one of the most significant debates in modern physics, the information paradox. When matter falls into a black hole, does the information it carries disappear forever, or is it somehow preserved? The ergosphere complicates this question. Since the region allows for energy extraction and particle interactions that differ from those near a non-rotating black hole, it might offer insights into how information behaves in such extreme environments. Could the ergosphere serve as a kind of buffer zone, where information is partially retained before being absorbed by the event horizon? Another avenue of exploration is the effect of magnetic fields in and around the ergosphere. Many rotating black holes, particularly those in the centers of active galaxies, are surrounded by powerful magnetic fields. These fields interact with the charged particles spiraling through the ergosphere, creating complex electromagnetic phenomena. Some of these interactions are thought to power the colossal jets of plasma that shoot out from black holes at nearly the speed of light. These jets are visible across billions of light years, making them some of the brightest and most energetic phenomena in the universe. By studying how the ergosphere contributes to these jets, scientists can learn more about the mechanics of black holes and their role in galactic evolution. Moreover, the ergosphere might be key to understanding certain types of high-energy astrophysical signals, such as fast radio bursts, FRBs, or ultra-high-energy neutrinos. These mysterious signals are often linked to extreme environments, and the ergosphere of a rotating black hole fits the bill perfectly. If such signals are indeed generated within or near the ergosphere, they could provide invaluable data about the physical conditions in this bizarre region. The philosophical implications of the ergosphere are equally profound. Its very existence challenges our perceptions of what is possible in the universe. In a sense, the ergosphere is a boundary between chaos and order, a region where the rules of physics are both upheld and bent to their breaking point. It's a reminder that the universe is not just a place of order and predictability, but also of unpredictability and wonder. For instance, what does it mean for spacetime to be dragged? This concept defies our intuitive understanding of space as a fixed, unchanging backdrop. The ergosphere teaches us that spacetime is dynamic, mutable, and deeply intertwined with the matter and energy it contains. This realization forces us to rethink our place in the universe, challenging the notion of a stable, unchanging cosmos. The ergosphere also has implications for the future of artificial intelligence and robotics. If we ever develop the technology to explore these regions, it's likely that human beings won't be the ones venturing into the ergosphere directly. Instead, we'll rely on highly advanced robotic probes and artificial intelligences capable of processing data and making decisions in real time. These machines would need to navigate the complexities of the ergosphere's twisted spacetime, avoid the event horizon, and carry out precise scientific experiments. The data they return could revolutionize our understanding of physics, perhaps even leading to new technologies we can't yet imagine. The more we study the ergosphere, the clearer it becomes that it's not just a region of theoretical interest, it's a key to unlocking some of the deepest mysteries of the cosmos. Its study unites multiple fields of science, from astrophysics and quantum mechanics to materials science and engineering. It also raises questions that challenge the very foundations of our understanding, such as the nature of time, the limits of energy, and the interconnectedness of matter and spacetime. In this sense, the ergosphere is not just a destination for scientific exploration, it's a symbol of the human quest for knowledge. It represents our willingness to push boundaries, to confront the unknown, and to embrace the complexity and beauty of the universe. Whether or not we ever set foot, or send a probe, into the ergosphere, its mysteries will continue to inspire us, driving new generations of scientists, thinkers, and dreamers to explore the cosmos. The ergosphere, with its blend of mystery, danger, and potential, is a testament to the power of curiosity. It challenges us to imagine what lies beyond the limits of our knowledge and to dream of a future where we might finally unlock the secrets of these cosmic whirlpools. Until then, it remains a place of wonder, a reminder that the universe is as vast and strange as our imaginations dare to make it. The ergosphere's allure grows not just from its physical and scientific characteristics but also from its role as a cosmic boundary between what is currently knowable and what lies beyond the reach of our most advanced theories. Its very existence provokes questions about the malleability of space and time, forcing us to reconsider the laws of nature that seem so immutable in our everyday experiences. The ergosphere, in essence, is not just a region of scientific interest but also a philosophical enigma that touches on the deepest questions of reality itself. One of the ergosphere's most fascinating implications is its potential to challenge our understanding of causality. Causality, the principle that cause precedes effect, is a cornerstone of modern physics and our perception of the universe. However, the ergosphere's twisted spacetime could, theoretically, create closed time-like curves, paths through spacetime that loop back on themselves. This raises the tantalizing possibility of time travel, albeit under conditions so extreme they remain purely speculative for now. Imagine, for instance, a particle or a spacecraft entering the ergosphere and being influenced by the warped spacetime in such a way that it completes a loop and returns to its starting point before it departed. Such a scenario would upend our understanding of linear time and introduce profound paradoxes, like the famous grandfather paradox. While these ideas remain deeply theoretical and face significant challenges from both physics and logic, they highlight the ergosphere's ability to stretch our imaginations to their limits. The concept of closed time-like curves within the ergosphere isn't just a playground for thought experiments. It also provides a framework for testing the boundaries of general relativity. If such curves are possible, even theoretically, they must comply with Einstein's equations. Yet, their implications might suggest areas where these equations break down or require modification. This could, in turn, guide physicists toward a more unified theory of the universe, one that reconciles general relativity with quantum mechanics. Even as the ergosphere offers tantalizing possibilities for energy extraction and time manipulation, it also serves as a crucible for testing the durability of physical laws. The extreme gravitational and rotational forces in this region create conditions that stretch these laws to their breaking points. For instance, how does the interaction between particles and spacetime within the ergosphere influence the fundamental constants of nature? Are these constants truly constant, or could they vary in such extreme environments? The answers to these questions could have far-reaching implications. If fundamental constants like the speed of light or Planck's constant were found to vary in the ergosphere, it would rewrite our understanding of physics and potentially reveal new dimensions of reality. Such discoveries would ripple outward, influencing everything from cosmology to particle physics, and even the technologies we develop in the future. The ergosphere is also a testing ground for the interplay between gravity and electromagnetism. In this region, the intense gravitational forces are accompanied by equally extreme magnetic fields, particularly around black holes that accrete matter from their surroundings. These magnetic fields interact with charged particles, producing phenomena that are not only fascinating but also visible across vast distances. Jets of plasma, accelerated to near-light speeds, are one of the most spectacular examples of this interaction. These jets, often emanating from the poles of a black hole, can stretch for thousands of light years, creating some of the most luminous structures in the universe. While these jets are typically associated with the accretion disk around a black hole, the ergosphere plays a critical role in their formation. The rotational energy extracted from the ergosphere helps power these jets, making them an observable signature of the extreme physics at play. Interestingly, these jets also provide a way to study black holes and their ergospheres indirectly. By analyzing the composition, velocity, and structure of the jets, scientists can infer properties of the black hole, such as its spin rate and the orientation of its axis. This is particularly useful for studying black holes that are too distant or obscure to be observed directly. The ergosphere's effects on matter and energy extend to the accretion disk, the swirling ring of gas and dust that often surrounds a black hole. The intense gravitational forces near the ergosphere heat this material to millions of degrees, causing it to emit high-energy radiation, including X-rays and gamma rays. These emissions provide another indirect method for studying the ergosphere, as well as the processes occurring within it. Moreover, the interaction between the ergosphere and the accretion disk may play a role in regulating the growth of black holes. By extracting energy from the black hole's rotation, the ergosphere could influence the rate at which matter falls into the event horizon. This, in turn, affects the black hole's mass and spin, creating a feedback loop that shapes its evolution over time. The ergosphere's role in the larger cosmic ecosystem cannot be overstated. By influencing the behavior of matter and energy in its vicinity, it affects everything from the dynamics of nearby stars to the structure of entire galaxies. In some cases, the energy extracted from the ergosphere might even contribute to the creation of new stars, as the outflows of material and energy trigger star formation in surrounding regions. At the same time, the ergosphere raises questions about the ultimate fate of black holes and the universe itself. If energy can be extracted from a black hole's spin, could this process eventually lead to the black hole's spinning down and losing its rotational energy entirely? And if so, what would this mean for the black hole's structure and its interaction with the surrounding universe? These questions tie into broader debates about the long-term evolution of the cosmos. As black holes slowly lose mass through Hawking radiation and potentially through processes like the Penrose mechanism, they might eventually evaporate entirely. The ergosphere, with its unique properties, could play a role in accelerating this process, contributing to the eventual dissolution of these cosmic giants. The ergosphere's role in the potential spin down of black holes offers a fascinating glimpse into the life cycle of these enigmatic objects. If energy extraction mechanisms like the Penrose process or Blandford's Najek mechanism can effectively drain rotational energy from a black hole, it raises intriguing questions about how this impacts the surrounding spacetime and the black hole itself. A spun-down black hole, stripped of its angular momentum, would transition into a non-rotating, spherically symmetric Schwarzschild black hole. This transformation not only alters the black hole's immediate properties, but also its ability to interact with its environment. The loss of rotational energy could diminish the black hole's ability to sustain the energetic jets often observed emanating from its poles. Without the rotational dynamics to power these outflows, the surrounding regions may experience reduced activity, potentially altering the balance of matter and energy on a galactic scale. Galaxies hosting such dormant black holes might see a slowdown in star formation triggered by the diminished jet-driven turbulence in interstellar gas clouds. On the other hand, the ergosphere's capacity for energy extraction also raises tantalizing possibilities for advanced civilizations. If humanity, or another intelligent species, could harness the energy from rotating black holes, it would open an era of unprecedented technological advancement. The energy output of even a small black hole's ergosphere dwarfs anything achievable by conventional means. Such an energy source could revolutionize space exploration, powering interstellar travel or even megastructures capable of sustaining entire civilizations. To put this into perspective, consider the energy potential of the Penrose process. By sending a spacecraft or engineered object into the ergosphere and carefully managing its trajectory, it might be possible to extract a significant fraction of the black hole's rotational energy. The process would rely on precise calculations to ensure that this split particle or object falls into the event horizon while the other escapes with more energy than it entered. Though far from practical with our current technology, the physics behind this concept remains sound. Beyond the technological implications, the ergosphere also serves as a natural laboratory for studying extreme physics. It offers a rare glimpse into the interplay between general relativity and quantum mechanics, two pillars of modern physics that remain fundamentally incompatible. The intense gravitational and rotational forces within the ergosphere create conditions where these theories overlap, potentially offering insights into their unification. For instance, the behavior of quantum fields within the ergosphere could reveal subtle deviations from predictions made by classical general relativity. Such deviations might point toward the existence of a more comprehensive theory of gravity, one that incorporates quantum effects. The discovery of such a theory would not only deepen our understanding of black holes but also provide clues about the nature of the universe itself. The ergosphere's significance extends even further when considering its role in the generation of gravitational waves. As matter interacts with the black hole's rotation, it can produce ripples in the fabric of spacetime that propagate outward at the speed of light. These gravitational waves carry information about the black hole's mass, spin, and the dynamics of its surroundings, offering a unique way to study these objects. The detection of gravitational waves by observatories like LIGO and Virgo has already revolutionized our understanding of black holes and other extreme cosmic events. By focusing on the signals originating from regions near the ergosphere, scientists could gain unprecedented insights into the rotational dynamics of black holes and the processes occurring within their warped spacetime. Interestingly, the ergosphere's ability to drag spacetime also provides a unique lens through which to study the effects of frame dragging. This phenomenon, predicted by general relativity, occurs when a massive, rotating object distorts the spacetime around it. In the case of the ergosphere, the frame dragging is so extreme that it forces objects within this region to move in the direction of the black hole's rotation. Studying this effect could yield valuable information about the fundamental properties of spacetime and its interaction with matter. The study of the ergosphere also has implications for our understanding of the early universe. Black holes are thought to have played a significant role in the formation of galaxies and the large-scale structure of the cosmos. By examining how the ergosphere influences matter and energy, scientists can gain insights into the processes that shaped the universe in its infancy. Additionally, the ergosphere might hold clues about the mysterious phenomenon of dark energy. This enigmatic force, which is driving the accelerated expansion of the universe, remains one of the greatest mysteries in modern physics. While the connection between dark energy and black holes is still speculative, the extreme conditions within the ergosphere could provide a testing ground for hypotheses that link these phenomena. As we push the boundaries of our understanding, the ergosphere continues to captivate scientists and philosophers alike. Its unique properties challenge conventional wisdom and invite us to explore the limits of what is possible. Whether through its implications for energy extraction, its role in testing fundamental theories, or its potential as a window into the early universe, the ergosphere stands as a testament to the power and mystery of the cosmos. The ergosphere's significance is not merely academic. It has the potential to inspire future generations to look toward the stars with a sense of wonder and curiosity. By studying this enigmatic region, we are reminded of the vastness of the universe and our small but significant place within it. The ergosphere serves as a reminder that even in the face of the unknown, humanity's capacity for discovery and innovation knows no bounds. The ergosphere's allure persists as one of the most perplexing regions of spacetime, urging us to question the very nature of existence. Its ability to twist space and time beyond recognition is both a scientific puzzle and a philosophical enigma. The interplay of extreme rotation, gravitational forces, and warped spacetime is not merely a curiosity for theoretical physics, but a gateway to understanding the universe at its most fundamental level. For instance, consider the role of the ergosphere in the evolution of black holes themselves. The energy extracted from the ergosphere might regulate how black holes grow and interact with their surroundings. Over time, as rotational energy is depleted, the black hole could become less active, potentially influencing the dynamics of nearby celestial systems. This energy transfer could even explain why some galaxies exhibit more pronounced central black hole activity than others, highlighting the ergosphere's indirect yet profound influence on cosmic architecture. Moreover, The ergosphere may hold secrets about one of the most profound mysteries in cosmology, the relationship between black holes and the fabric of spacetime itself. Scientists have long debated whether black holes represent singularities, points where spacetime curvature becomes infinite, or whether they are manifestations of deeper, hidden layers of reality. The ergosphere, as a transitional region between normal spacetime and the black hole's event horizon, could offer clues about the true nature of these enigmatic objects. Some theories suggest that the ergosphere might act as a bridge to other dimensions or parallel universes. If spacetime is dragged to the extent that it allows for the creation of wormholes or other exotic structures, the ergosphere could serve as a cosmic portal, connecting distant regions of the universe or even different universes entirely. While these ideas remain speculative, they are grounded in the extreme physics of the ergosphere, where traditional rules of spacetime begin to break down. The ergosphere's potential to serve as a gateway is not limited to theoretical constructs like wormholes. It might also reveal the existence of entirely new particles or fields. The intense energy and gravitational gradients in this region could create conditions where particles behave in ways never observed elsewhere. This includes the possible emergence of particles predicted by quantum field theories but not yet detected, such as axions or gravitons. Discovering such particles within the ergosphere would not only expand our understanding of particle physics, but also offer insights into the unification of quantum mechanics and general relativity. Beyond its role in shaping the evolution of black holes and revealing new physics, the ergosphere also invites us to rethink the concept of entropy. In thermodynamics, entropy is often associated with disorder and the irreversible flow of energy. However, the ergosphere challenges this notion by allowing energy to be extracted in highly organized ways, such as through the Penrose process. This raises questions about how entropy operates in extreme environments, and whether our current understanding of this fundamental concept is incomplete. For example, if rotational energy can be extracted from the ergosphere without violating the second law of thermodynamics, it suggests that the boundaries of entropy are more flexible than previously thought. This flexibility could have profound implications for understanding not only black holes, but also the broader mechanisms that govern the universe. It might even offer new perspectives on the ultimate fate of the cosmos, particularly in scenarios where entropy reaches its maximum limit, a state known as heat death. The ergosphere also provides a unique context for exploring the nature of information in the universe. The famous information paradox, which questions whether information is lost when matter falls into a black hole, remains one of the most debated topics in theoretical physics. Some researchers propose that the ergosphere might play a role in preserving or transmitting this information, acting as an intermediary region where information is transformed but not destroyed. For instance, the rotational dynamics of the ergosphere could encode information about matter and energy interactions in ways that remain accessible to the outside universe. This idea aligns with the holographic principle, which posits that all the information contained within a three-dimensional region of space can be represented on its two-dimensional boundary. The ergosphere, as a boundary-like region with unique properties, could serve as a testing ground for this principle, offering a potential resolution to the information paradox. The ergosphere's role in the information paradox also ties into broader questions about the fundamental nature of reality. If the ergosphere can encode and preserve information, it challenges the notion that black holes are ultimate destroyers of matter and energy. Instead, they might be seen as cosmic recyclers, transforming and redistributing information across the universe in ways we are only beginning to understand. This perspective has profound implications for the study of cosmology and the origin of the universe. If black holes, through mechanisms like the ergosphere, play a role in preserving and redistributing information, they could be integral to the universe's long-term evolution. Some theories even suggest that black holes might serve as seeds for new universes, with the ergosphere acting as a transitional region where information from one universe is transformed and carried into another. Such ideas, while speculative, highlight the ergosphere's potential to bridge the gap between theoretical physics and metaphysical questions about existence. By studying this region, we are not just exploring the mechanics of black holes but also delving into the deepest mysteries of the cosmos, including the nature of time, space, and reality itself. The ergosphere's potential to inspire is matched only by the challenges it presents. Observing and studying this region directly is an immense technical hurdle, given its extreme conditions and proximity to the event horizon. However, advancements in observational astronomy, such as the Event Horizon Telescope, bring us closer to capturing the dynamics of the ergosphere in unprecedented detail. These efforts promise to illuminate this enigmatic region and deepen our understanding of the universe's most extreme phenomena. The ergosphere's observational challenges underscore its unique position at the intersection of theory and experimentation. While direct visualization remains elusive, the effects of the ergosphere can be inferred from the phenomena it influences. For example, the powerful jets of high-energy particles often observed near rotating black holes are likely driven by processes occurring within the ergosphere. These jets, which extend for thousands of light-years, provide indirect evidence of the energy extraction mechanisms that operate in this region. Advanced telescopes, such as the Event Horizon Telescope, EHT, aim to capture images of black holes and their immediate environments. The groundbreaking image of the supermassive black hole at the center of the galaxy M87 in 2019 showcased the shadow of the black hole, surrounded by a glowing ring of hot gas. While this image primarily highlighted the photon ring and the event horizon, future iterations of such technology might reveal more about the ergosphere's dynamics, particularly the way it drags spacetime and influences nearby matter. Beyond observational efforts, computer simulations play a crucial role in unraveling the mysteries of the ergosphere. These simulations, powered by the equations of general relativity, allow scientists to model the behavior of matter and energy in the extreme conditions near a rotating black hole. By studying these models, researchers can gain insights into how the ergosphere interacts with its surroundings and how energy extraction processes unfold. One intriguing outcome of these simulations is the realization that the ergosphere's boundaries are not static. Instead, they fluctuate based on the black hole's rotation, the infall of matter, and other external factors. These dynamic boundaries suggest that the ergosphere is a highly active region, constantly reshaped by the interplay of forces acting upon it. This dynamic nature could have far-reaching implications for how black holes evolve and interact with their environments over time. Another fascinating aspect of the ergosphere is its potential role in the synthesis of heavy elements. The extreme conditions within this region could facilitate nuclear reactions that are otherwise impossible in more stable environments. As matter spirals into the ergosphere, it experiences immense compression and heating, potentially leading to the formation of elements heavier than those produced in stars or supernovae. If this hypothesis is correct, the ergosphere could be a key player in the cosmic alchemy that creates the building blocks of planets and life. The ergosphere also holds promise for advancing our understanding of exotic states of matter. The intense gravitational and rotational forces in this region could compress matter to densities beyond those found in neutron stars, possibly creating forms of matter that exist only in theory. These states, such as quark-gluon plasma or strange matter, could provide a glimpse into the conditions that prevailed in the early universe, shortly after the Big Bang. Moreover, the ergosphere's unique properties invite speculation about its potential as a testing ground for the unification of quantum mechanics and general relativity. The physics of black holes, and particularly the ergosphere, pushes both theories to their limits, revealing inconsistencies that must be resolved to achieve a comprehensive understanding of the universe. By studying the interactions between quantum particles and the curved spacetime of the ergosphere, scientists might uncover clues that lead to a unified theory of quantum gravity. This quest for unification also intersects with philosophical questions about the nature of time. The ergosphere's ability to drag spacetime creates a scenario where time itself is distorted, challenging our intuitive understanding of causality and chronology. Within the ergosphere, time does not flow uniformly. Instead, it is stretched and compressed in ways that depend on an object's trajectory and velocity. These effects could offer insights into the fundamental structure of time and its relationship to the fabric of the universe. The ergosphere's time-warping properties also have practical implications for space exploration. If future spacecraft could navigate the ergosphere safely, they might exploit its time dilation effects to perform experiments, or travel vast distances. For instance, an astronaut spending a short time in the ergosphere could return to find that much more time has passed outside, a phenomenon similar to what is predicted by the theory of relativity for objects near strong gravitational fields. Such a scenario, while currently theoretical, highlights the ergosphere's potential as a natural time machine. Additionally, the ergosphere's influence on light offers another avenue for exploration. As photons enter this region, they are bent and stretched by the intense gravitational forces, creating phenomena like gravitational lensing and redshift. These effects can provide valuable information about the black hole's properties, including its spin, mass, and angular momentum. By analyzing the light emitted or reflected from the ergosphere, astronomers can piece together a more complete picture of its dynamics. The potential for energy extraction from the ergosphere also raises ethical and philosophical questions. If humanity or other advanced civilizations were to harness this energy, how might it be used? Would it fuel scientific progress and exploration, or could it become a source of conflict and exploitation? These questions echo broader concerns about the responsible use of technology and the balance between progress and preservation. The ergosphere's implications extend even to the realm of existential risk. Black holes, with their immense power and mystery, have long captured the human imagination as symbols of destruction and rebirth. The ergosphere, as a region where energy can be extracted and transformed, challenges this perception, offering a more nuanced view of black holes as both creators and destroyers. By studying the ergosphere, we confront not only the physical limits of the universe but also the boundaries of our own understanding and imagination. Ultimately, the ergosphere represents a frontier in every sense of the word. It is a place where the known and the unknown collide, where the laws of physics are tested, and where the possibilities for discovery seem boundless. As we continue to explore this enigmatic region, we are reminded of the endless curiosity that drives us to look to the stars and ask the most profound questions about our place in the cosmos. The ergosphere's status as a frontier of discovery is also emblematic of humanity's enduring quest to understand the universe. It is a region that challenges not only our scientific capabilities but also our philosophical perspectives. In a realm where space and time are twisted into incomprehensible shapes, our very notions of reality are put to the test. This makes the ergosphere a unique laboratory, not just for physics but for understanding the limits of human cognition and imagination. One of the most profound philosophical questions raised by the ergosphere is the concept of determinism. In classical physics, the universe operates like a clockwork machine, with every event having a definite cause. But within the ergosphere, the interplay of extreme gravitational and rotational forces creates a level of unpredictability. Particles and photons caught in this region can follow paths that seem almost random, influenced by the chaotic dynamics of spacetime. This has led some theorists to speculate that the ergosphere could be a natural example of quantum chaos on a macroscopic scale. This chaotic behavior introduces fascinating implications for the study of entropy. The second law of thermodynamics states that entropy, or disorder, always increases in a closed system. However, the energy extraction processes theorized for the ergosphere, such as the Penrose process, appear to locally reduce entropy by converting chaotic energy into more ordered forms. This paradox challenges our understanding of how entropy behaves in extreme environments, and could lead to a deeper understanding of the relationship between energy, matter, and information. The information paradox itself finds a potential battleground in the ergosphere. Black holes are infamous for their mysterious treatment of information. According to classical general relativity, anything that crosses the event horizon is lost forever, taking its information with it. However, quantum mechanics insists that information cannot be destroyed. The ergosphere, sitting on the boundary between the accessible and the inaccessible, might provide a unique setting to study how information is processed, stored, or even retrieved in the vicinity of black holes. Some scientists propose that the ergosphere could serve as a conduit for information exchange between our universe and other potential dimensions or realities. The space-time warping and frame-dragging effects in this region create conditions that might allow for interactions with realms beyond our three-dimensional space. While these ideas remain speculative, They are rooted in legitimate questions about the nature of reality and the possibilities for interdimensional connectivity. These considerations lead us to the topic of black hole thermodynamics, a field that combines quantum mechanics, general relativity, and thermodynamics. The ergosphere, as an energy-rich and highly dynamic region, plays a pivotal role in this field. The concept of black hole temperature, first introduced by Stephen Hawking, suggests that black holes emit radiation and slowly lose mass over time. The ergosphere's energy extraction mechanisms might influence this radiation, adding another layer of complexity to our understanding of black hole evaporation. Another compelling aspect of the ergosphere is its potential connection to wormholes, hypothetical tunnels through spacetime that could allow for faster-than-light travel or shortcuts between distant regions of the universe. Some theorists speculate that the extreme conditions in the ergosphere could either stabilize existing wormholes or create the conditions necessary for their formation. If true, this would make the ergosphere a critical area of study for anyone interested in the possibility of interstellar or intergalactic travel. The interplay between the ergosphere and quantum mechanics also opens the door to discussions about quantum entanglement. This phenomenon, where particles become interconnected in such a way that the state of one instantly affects the state of another, even across vast distances, could have unique manifestations in the ergosphere. The intense gravitational and rotational forces in this region might influence the behavior of entangled particles, providing new insights into the relationship between gravity and quantum mechanics. As we venture further into these speculative realms, it's essential to ground our understanding in observable phenomena. The ergosphere, despite its theoretical complexity, has tangible effects on its surroundings. For instance, the accretion disks of matter spiraling into black holes often exhibit behaviors that can be linked to the ergosphere. These disks, heated to extreme temperatures, emit powerful X-rays and other forms of radiation, offering a window into the high-energy processes at work. The radiation emitted by these accretion disks could carry imprints of the ergosphere's dynamics. By analyzing the spectra of this radiation, scientists can infer properties like the spin rate of the black hole and the distribution of matter within the ergosphere. This type of analysis is already being used to study black holes in our galaxy and beyond, providing indirect evidence of the ergosphere's influence. Another area of active research is the interaction between the ergosphere and magnetic fields. Many black holes are surrounded by magnetic fields that can become twisted and amplified by the frame-dragging effects of the ergosphere. These interactions could play a crucial role in the formation of jets and other energetic phenomena observed near black holes. By studying these magnetic interactions, scientists hope to uncover the mechanisms that drive some of the most powerful events in the universe. The ergosphere's potential for energy extraction also has implications for the search for extraterrestrial intelligence. If advanced civilizations exist, they might have discovered ways to harness the energy of rotating black holes via the ergosphere. The signatures of such activities, such as unusually structured radiation or unexpected gravitational waves, could serve as indicators of intelligent life elsewhere in the cosmos. This possibility adds a layer of excitement to the study of the ergosphere, linking it to one of humanity's most profound questions: are we alone in the universe? The ergosphere's mysteries extend beyond the purely scientific, touching on questions of human aspiration and ingenuity. It represents a boundary where our current understanding meets the unknown, a challenge that inspires the next generation of physicists, engineers, and dreamers. As we continue to explore this enigmatic region, we are reminded of the boundless potential of human curiosity and the transformative power of scientific discovery. As we delve deeper into the ergosphere and its extraordinary properties, we are drawn into an ever-expanding universe of possibilities. The ergosphere, as we have seen, represents an intersection between known and unknown, a place where the laws of physics as we currently understand them are stretched, twisted, and redefined. This is a region that forces us to reconsider fundamental principles of reality itself, from the nature of space and time to the flow of energy, and the behavior of matter under extreme conditions. One area of particular interest in the study of the ergosphere is its potential for influencing the structure of spacetime itself. The frame-dragging effect, the way in which rotating black holes pull spacetime along with them, raises questions about the very fabric of the universe. According to Einstein's theory of general relativity, mass and energy curve spacetime, and the ergosphere amplifies this effect to a remarkable degree. This curving of spacetime is not merely a passive phenomenon but actively shapes the movement of objects within it. In essence, the ergosphere is like a cosmic whirlpool, pulling everything into its orbit, from stars and gas to light and even the very fabric of spacetime. This intense distortion of spacetime suggests that the very structure of the universe is more flexible and dynamic than we might have imagined. It's as though the universe itself is fluid, constantly being molded and reformed by the powerful forces within black holes. This notion of spacetime being a malleable, interactive entity opens up exciting new lines of thought for theoretical physics. The effects of the ergosphere could shed light on other cosmic phenomena that seem to defy conventional understanding. For instance, the connection between black holes and the concept of singularities, where spacetime curvature becomes infinite, might be better understood through the study of frame dragging and the unique distortions that occur within the ergosphere. Furthermore, these insights into the malleability of spacetime raise profound questions about the very origins of the universe itself. Could the forces at work within the ergosphere hold the key to understanding the birth of spacetime in the Big Bang? Could it be that the very early universe existed in a state similar to the chaotic, high-energy environment of a black hole's ergosphere, where space and time were fluid, constantly being reshaped by gravitational forces? Exploring these questions takes us into the realm of quantum gravity, a field that seeks to unite the laws of general relativity with the principles of quantum mechanics. The ergosphere provides an ideal environment to study how quantum effects might manifest in the presence of extreme gravitational fields. This fusion of the largest and smallest scales of the universe could lead to breakthroughs that are as transformative as the development of quantum theory itself. In the context of energy extraction, another fascinating implication of the ergosphere is the potential for practical applications in the distant future. While we are far from harnessing the power of black holes, the theoretical framework for extracting energy from the ergosphere offers tantalizing possibilities. If we can figure out how to tap into the rotational energy of black holes, we could potentially have access to a nearly unlimited source of power. One of the most promising methods for energy extraction from the ergosphere is the Penrose process, which, as previously discussed, involves splitting particles into two. One of these particles is ejected with more energy than the original, while the other falls into the black hole. The energy difference between the two particles can theoretically be harnessed, providing a method of tapping into the immense rotational energy of the black hole. Though the practical challenges of this process are currently insurmountable, it is a field of active research that could have profound implications for future space exploration and energy generation. As we consider the implications of the ergosphere on space travel, it's essential to think about how it could revolutionize our approach to interstellar journeys. With the energy extraction possibilities in mind, advanced civilizations might find a way to power intergalactic travel by exploiting the power of black holes. This could enable spacecraft to travel across vast distances that currently take thousands, or even millions of years. It is not just a theoretical possibility, but a glimpse into a future where the mysteries of black holes are not merely objects of scientific fascination, but practical resources for the survival and advancement of civilizations. However, the ergosphere's role in space travel would not just be about harnessing energy. Its effects on spacetime could also have profound implications for the way we understand movement through the cosmos. The warping of spacetime caused by a rotating black hole could create potential shortcuts through the universe, in the form of wormholes. These theoretical tunnels in spacetime could allow for faster-than-light travel by creating direct paths between distant points in space. If we are able to understand and manipulate the frame-dragging effects of the ergosphere, we might one day be able to use it to traverse the vast distances between stars and galaxies. This idea of wormholes and shortcuts in spacetime is not purely speculative. It has roots in Einstein's theory of general relativity, and many physicists believe that wormholes could exist, even if they are yet to be discovered. The ergosphere, with its extreme warping of spacetime, might provide the ideal environment for these structures to form. If wormholes do exist in the universe, the ergosphere could be a key to unlocking their secrets, potentially offering humanity a way to travel across the universe in ways we can barely imagine. While the ergosphere represents an incredible potential for discovery, it also comes with its own set of dangers. The very forces that make it an intriguing subject of study also make it incredibly hazardous to approach. The sheer intensity of the gravitational field, combined with the high-energy radiation from the accretion disk, would make it impossible for any spacecraft to safely venture into the ergosphere without advanced shielding or propulsion systems far beyond what we currently possess. Additionally, the behavior of matter and radiation in this region is unpredictable, making any attempt to explore it fraught with risk. Despite these challenges, the ergosphere remains one of the most exciting areas of astrophysics today. It offers us a unique opportunity to study the interplay between gravity, energy, and the fabric of spacetime. By understanding this dynamic and often chaotic region, we can gain insights into some of the deepest mysteries of the universe, including the nature of black holes, the origins of the universe, and the potential for energy extraction and interstellar travel. As we continue to probe the mysteries of the ergosphere, we are reminded of the incredible resilience of human curiosity. Our ability to push the boundaries of what is known and explore the farthest reaches of the cosmos is a testament to our unyielding desire to understand the universe in all its complexity. The ergosphere, with its profound implications for physics, technology, and even the future of human civilization, stands as a symbol of our endless quest for knowledge and discovery. As we continue to explore the incredible nature of the ergosphere, it's important to understand that the implications of this region extend far beyond our ability to extract energy or travel through space. The study of the ergosphere may ultimately challenge and redefine some of our deepest assumptions about the universe itself. At the heart of the ergosphere's mystery lies the profound relationship between matter and energy. The extreme rotational velocities of black holes create such intense gravitational effects that even light cannot escape. This forces us to think about the very nature of light and energy, pushing the limits of our understanding of physics. We are accustomed to thinking of light as something that moves freely through space, independent of gravitational influences. However, within the ergosphere, light is not merely affected by gravity, it becomes trapped in a dance with the black hole, spiraling inward along with all other matter. This leads to fascinating questions about the very nature of energy, and whether it is truly free or ultimately governed by the same gravitational forces that dictate the fate of the objects we see in the universe. The ergosphere thus challenges our preconceived ideas about space, time, and the laws of physics. It suggests that what we perceive as the rules of reality are more fluid and dynamic than we might have believed. In some ways, it forces us to confront a humbling truth: our knowledge is limited by the constraints of the physical world we experience. To understand black holes and the ergosphere, we must push the boundaries of this knowledge, looking beyond the familiar to the strange and mysterious workings of the cosmos. Perhaps the most fascinating aspect of the ergosphere is how it opens up new possibilities for understanding the nature of black holes themselves. Traditionally, black holes have been viewed as singularities, regions of infinite density and curvature where the laws of physics break down. The ergosphere, however, suggests that even within these extreme environments, there may be new opportunities for discovery. The frame-dragging effects, the twisting of spacetime, and the dynamic relationship between energy and matter all hint at deeper mysteries that we have yet to uncover. In the distant future, as our understanding of quantum mechanics continues to evolve, we may find that the ergosphere offers a way to reconcile some of the contradictions between general relativity and quantum theory. One of the most significant challenges in modern physics is finding a way to unite these two pillars of science, and the study of black holes, and specifically the ergosphere, could be the key. The extremity of the gravitational fields, the quantum effects that occur at such high energies, and the intricate behavior of matter within the ergosphere could provide insights that allow us to bridge the gap between the large and small scales of the universe. It's also worth considering the potential technological breakthroughs that could emerge from studying the ergosphere. As mentioned earlier, energy extraction from black holes is a tantalizing possibility. If we can figure out how to harness the rotational energy of a black hole through processes like the Penrose process, we could unlock a new form of energy generation. This form of energy would be orders of magnitude more powerful than anything we have access to today. Theoretically, it could provide an almost limitless supply of energy for human civilization, potentially allowing us to power entire star systems. To put this into perspective, the Sun produces energy by converting mass into energy through nuclear fusion. This process, while incredibly powerful, is limited by the amount of fuel the Sun can burn over its lifespan. A black hole, on the other hand, is essentially an infinitely dense reservoir of energy. The amount of energy that could theoretically be extracted from the ergosphere could power entire civilizations, enabling humanity to colonize the stars and venture into the far reaches of the galaxy. Of course, we are still far from the ability to extract energy from black holes in any practical way. The technology required to achieve this level of energy production would need to be far more advanced than anything we have today. However, the very idea that such a possibility exists underscores the importance of studying the ergosphere and the broader field of black hole physics. These seemingly abstract concepts could hold the key to some of the greatest challenges facing humanity in the coming centuries. While much of the discussion around black holes and the ergosphere has focused on energy extraction, we cannot overlook the more fundamental aspects of black hole physics that are so crucial to our understanding of the universe. The study of black holes, and in particular the ergosphere, could provide insights into the very structure of spacetime itself. We have already seen how the rotational motion of black holes distorts the fabric of spacetime, and there are indications that this effect could extend to other areas of physics as well. For example, the study of black hole mergers, when two black holes collide and combine into a single, more massive black hole, has opened up new possibilities for understanding how space and time behave under extreme conditions. These mergers produce gravitational waves, ripples in spacetime itself, that can be detected by instruments like LIGO, Laser Interferometer Gravitational Wave Observatory. These waves provide us with a new way to study the universe, offering a direct glimpse into the nature of spacetime and the behavior of black holes. The study of black hole mergers is still in its infancy, but it has already revolutionized our understanding of the universe. The first detection of gravitational waves in 2015, which resulted from the merger of two black holes, marked a groundbreaking moment in astrophysics. Since then, scientists have continued to study these waves, learning more about the properties of black holes and the fundamental nature of spacetime. This is just one example of how the ergosphere, as part of the broader study of black holes, is helping to push the boundaries of what we know about the universe. Looking ahead, the future of black hole research and the study of the ergosphere is incredibly exciting. The more we learn about the forces at play within these mysterious objects, the more we realize that we are only scratching the surface of what is possible. As technology continues to advance, and as our understanding of the universe deepens, it is likely that we will uncover even more surprises hidden within the black hole's grip. For instance, the development of more advanced space telescopes and observatories could allow us to study the behavior of black holes in even greater detail. The Event Horizon Telescope, which captured the first ever image of a black hole's event horizon in 2019, represents a significant step forward in this effort. Future missions could provide us with even more detailed images and data, allowing us to study the ergosphere directly and learn more about its effects on spacetime and matter. We may also see advancements in our ability to simulate black hole environments using powerful supercomputers. These simulations could help us better understand the extreme conditions of the ergosphere and provide insights into how black holes interact with their surroundings. By creating virtual models of black holes, we could gain a deeper understanding of how these objects work, ultimately leading to breakthroughs in both theoretical and applied physics. In addition to technological advancements, the ongoing development of new theoretical frameworks could help to further our understanding of black holes and the ergosphere. The field of quantum gravity, which seeks to combine general relativity with quantum mechanics, holds great promise for unraveling the mysteries of black holes. As scientists continue to explore the intersection between these two domains of physics, we may find that the ergosphere plays a central role in unlocking the ultimate secrets of the universe. All of these developments, technological, theoretical, and observational, point to a future where the study of black holes and the ergosphere could have profound implications for science, technology, and even our understanding of the cosmos. The quest to understand black holes is not just about exploring distant regions of space. It is about understanding the very nature of reality itself. The ergosphere, as a dynamic and ever-changing region of spacetime, is at the heart of this quest, offering a glimpse into a universe far more complex and fascinating than we could have ever imagined. As we continue our deep dive into the ergosphere of black holes, the mysteries only grow more intriguing. The concept of energy extraction, framed by theories like the Penrose process, not only offers a potential goldmine of limitless energy, but it forces us to rethink the way we approach energy production itself. If we were to harness energy from the ergosphere, it wouldn't just change how we power our cities or spacecraft. It would transform the very foundation of our technology, opening the doors to unimaginable possibilities. To truly grasp the scale of what this means, we need to think beyond today's methods of energy generation. The idea that we could use the rotational energy of a black hole to fuel our civilization taps into the potential of a system that is more powerful than anything we've seen. The energy available in the ergosphere dwarfs anything we could ever hope to generate with nuclear fission, fusion, or even the most efficient renewable sources we have at our disposal. It's an amount of energy that could, in theory, power entire galactic empires. But the practicalities of harnessing such energy are still purely speculative. Before we can even begin to dream of tapping into this resource, we must first gain a deeper understanding of the mechanics of the ergosphere, and how it interacts with the surrounding space. At the center of these questions is the phenomenon of frame dragging. This is a crucial element in understanding the ergosphere, and it's something that challenges our very conception of how space-time operates. Frame dragging occurs when a massive rotating object, like a black hole, distorts the fabric of spacetime itself. Essentially, the black hole's spin drags spacetime along with it, causing everything near it to follow the same rotational direction. This effect is strongest at the event horizon, the boundary beyond which nothing, not even light, can escape. However, it extends into the ergosphere, a region where objects are forced to move in sync with the black hole's rotation. Imagine a spaceship venturing too close to a rotating black hole. In this region, not only would the ship feel the pull of the black hole's immense gravity, but it would also feel the effects of this frame dragging. The ship would be compelled to spin in the same direction as the black hole, unable to resist the drag of spacetime. The closer it gets to the event horizon, the more intense this effect would be, to the point where no matter what the ship does, it would be trapped in the rotation. This interplay of gravity and rotation has far-reaching consequences, not just for objects that enter the ergosphere, but for our understanding of spacetime itself. It suggests that the very structure of space and time may not be as rigid as we once thought. Instead of being separate and independent, space and time could be part of a more complex, interconnected whole. The ergosphere acts as a bridge between these two domains, where the normal rules of motion break down and where gravitational forces and rotational effects combine in ways that defy intuition. As we delve deeper into the scientific implications, we must acknowledge that the ergosphere also has the potential to teach us about the limits of physics. While the general theory of relativity does a remarkable job of explaining the behavior of objects near black holes, it doesn't tell the full story. In fact, some of the most perplexing phenomena surrounding black holes, like the behavior of matter and energy in the ergosphere, are difficult to reconcile with our current understanding of physics. This suggests that there may be new, unknown forces or phenomena at play in these regions of space. For example, the interaction between the intense gravitational fields in the ergosphere and quantum particles might be revealing new aspects of the universe. It is possible that the extreme environments around black holes are giving us glimpses into the workings of quantum gravity, a theory that seeks to unite general relativity with quantum mechanics. While we have made progress in understanding the fundamental forces of the universe, there are still significant gaps in our knowledge, gaps that could potentially be filled by studying black holes and the effects they have on spacetime. One of the more exciting possibilities that arises from this research is the potential connection between black holes and dark matter. Dark matter is one of the most elusive components of the universe. It cannot be seen directly, but its presence is inferred by its gravitational effects on visible matter. Some scientists have hypothesized that black holes, particularly those in the centers of galaxies, might play a role in the formation or behavior of dark matter. The frame-dragging effects in the ergosphere could potentially offer us a new way to observe and study dark matter indirectly, by examining how it behaves in the extreme gravitational fields around black holes. Similarly, black holes in the ergosphere could offer new insights into dark energy, another mysterious force that seems to be driving the accelerated expansion of the universe. The study of black holes could provide crucial clues about how these two unknown phenomena, dark matter and dark energy, interact with the visible matter and energy in our universe. This would represent a major breakthrough in our understanding of the cosmos, bringing us closer to a unified theory that explains all of the forces and particles that make up the universe. As fascinating as these theoretical implications are, we must also consider the practical challenges that come with studying black holes and the ergosphere. Despite the remarkable progress we've made in observational astronomy, black holes remain elusive objects. They are located far from Earth, and even the most powerful telescopes can't directly observe the interior of a black hole. Instead, scientists rely on indirect evidence, such as the behavior of nearby stars and the radiation emitted by matter as it is pulled into the black hole. However, the rapid advancements in gravitational wave astronomy are beginning to change the way we study black holes. As mentioned earlier, the detection of gravitational waves from black hole mergers marked a new era in astrophysical research. These ripples in spacetime provide us with an entirely new way to hear the universe, offering us insights into the behavior of black holes in ways that were previously unimaginable. In the future, as we continue to refine our instruments and methods for detecting gravitational waves, we may be able to study the ergosphere and other black hole phenomena in far greater detail. There is also the exciting prospect of using future space missions to observe black holes more directly. While current space telescopes can capture stunning images of distant galaxies and stars, they lack the resolution needed to study the fine details of black holes themselves. However, future observatories could be equipped with more advanced technology capable of studying black holes and their surrounding environments in much greater detail. This would allow us to explore the ergosphere and the complex interactions that take place within it. One of the most tantalizing possibilities lies in the future of space exploration. As we look beyond our own solar system, we may encounter more exotic environments where black holes and their ergospheres play a central role. Future missions to the outer reaches of the galaxy, or even beyond, could provide us with the opportunity to study black holes up close, perhaps even sending spacecraft into the ergosphere itself to study these regions firsthand. While such missions are far from reality, the advancements in technology and scientific understanding may one day make this possible. The more we learn about black holes, the ergosphere, and the nature of spacetime itself, the more we come to realize that the universe is far stranger and more complex than we could have ever imagined. The mysteries of the ergosphere offer us a window into a realm where the rules of physics seem to break down, challenging everything we know about the fabric of reality. Whether it's the potential for energy extraction, the insights into quantum gravity, or the new perspectives on dark matter and dark energy, the study of black holes and their enigmatic ergospheres holds the key to some of the greatest discoveries of the coming centuries. The mysteries surrounding the ergosphere and black holes continue to stretch the limits of our scientific imagination. As we venture deeper into understanding the nature of these cosmic phenomena, we begin to see how their study could revolutionize not just our knowledge of physics, but our entire approach to exploring the universe. The concept of extracting energy from the ergosphere through mechanisms like the Penrose process remains a tantalizing possibility, one that could one day fuel interstellar travel or provide unimaginable resources. Yet, the enormity of the challenges we face in trying to understand and harness this energy also becomes clearer. To comprehend the ergosphere's true significance, we must first appreciate the scale of the forces at play. In our everyday experience, gravity is a force that we feel pulling us toward the Earth, but it's easy to forget how truly powerful it can be when concentrated in an object as massive as a black hole. The gravitational forces near the ergosphere are so immense that they can bend not just the trajectories of objects, but the very fabric of spacetime itself. Spacetime, as described by Einstein's theory of general relativity, is not a static backdrop. It's a dynamic entity that can be curved and twisted by the presence of mass and energy. And when it comes to black holes, this curving of space-time reaches extreme levels that defy our conventional understanding. In the case of rotating black holes, also known as curved black holes, this curving becomes even more profound due to the combination of the black hole's mass and its rapid spin. As we discussed earlier, the ergosphere is the region surrounding a rotating black hole where space-time itself is dragged into the black hole's rotation. This dragging effect, known as frame dragging, extends far beyond the event horizon, allowing objects to gain energy as they move in the direction of the spin. But there's more to this story than just energy extraction. The very fabric of space-time in the ergosphere can be thought of as a kind of cosmic whirlpool. Picture a surface of water that's spinning rapidly, pulling objects along with it. As objects move through the ergosphere, they are essentially caught in the rotational flow of space-time itself. This leads to some truly mind-bending consequences. Not only do objects lose their ability to escape the black hole's pull if they pass within the event horizon, but within the ergosphere, the trajectories of objects are dictated by the spin of the black hole itself. This has implications for any object or spacecraft that comes too close. For example, if a probe were to venture into the ergosphere, it would find that no matter how it moves, it would be forced to rotate in the direction of the black hole. Any attempt to move against this spin would require an immense amount of energy that could be better used to extract resources or power spacecraft systems. However, the gravitational forces near the ergosphere aren't the only challenges faced by objects venturing into these extreme environments. The intense radiation near black holes, especially in regions like the accretion disk, can be another major hurdle. Accretion disks, which form from material that falls toward the black hole, can generate X-rays and other high-energy radiation as they are compressed and heated by the black hole's immense gravity. This radiation could easily overwhelm any spacecraft that ventures too close, making it extremely difficult to explore or harness resources from this region. Yet, despite these dangers, the potential rewards are enormous. By understanding how the ergosphere operates, scientists could one day develop methods for shielding spacecraft from harmful radiation, or better yet, they might discover ways to tap into the high-energy environment around black holes without risking destruction. This remains a goal far in the future, but it's one that holds immense potential for reshaping humanity's relationship with space travel. The exploration of black holes, particularly the regions around them, could also shed light on some of the most fundamental questions in physics. For instance, the nature of quantum mechanics and its relationship to gravity remains one of the biggest unsolved mysteries in modern science. The effects observed in the ergosphere, with its mixture of extreme gravitational fields and the potential for quantum effects, may offer clues as to how these two realms of physics can be reconciled. In fact, the study of black holes is one of the key areas where scientists hope to uncover a unified theory of quantum gravity, a theory that could explain both the large-scale structure of the universe and the behavior of the smallest subatomic particles. One of the most exciting developments in recent years has been the rise of gravitational wave astronomy. As we've seen, gravitational waves are ripples in spacetime caused by the acceleration of massive objects, like black holes, and their detection has opened a new window into the universe. By studying gravitational waves, scientists can now observe events like black hole mergers, where two black holes collide and release an immense burst of energy in the form of gravitational waves. These waves provide us with a direct link to some of the most extreme environments in the universe, offering an entirely new way to study the ergosphere and the phenomena that occur within it. One of the most important features of gravitational wave detection is that it allows scientists to probe black holes without the need for light. Since black holes themselves do not emit light, studying them using traditional methods, like optical telescopes, has always been challenging. But gravitational waves do not rely on light, and they can be detected even from black holes that are millions or billions of light years away. This gives us the ability to study black holes in ways that were once thought impossible. In the coming decades, advancements in gravitational wave detectors could provide even more detailed information about the ergosphere and the behavior of matter near black holes. The ability to detect and analyze these waves with greater precision will allow us to test the predictions of general relativity and learn more about the fundamental nature of spacetime. If we are lucky, we might even be able to observe the effects of objects moving through the ergosphere or the energy extraction processes in real time, giving us a deeper understanding of these enigmatic cosmic structures. Beyond the technical challenges, there are also philosophical and existential questions raised by the study of black holes and their ergospheres. The idea that space and time can be so radically distorted by a rotating black hole challenges our very understanding of reality. We tend to think of space and time as constants, as the unchanging stage on which the events of the universe unfold. But black holes remind us that these concepts are not fixed. They can be shaped and warped by the presence of massive objects. If space-time can be so distorted in the presence of a black hole, what does this say about the larger structure of the universe? Is it possible that the very fabric of the cosmos is more fluid and malleable than we ever imagined? This question leads us into the realm of cosmology, the study of the universe as a whole. Black holes, particularly the ones at the centers of galaxies, are thought to play a crucial role in the formation and evolution of galaxies. Some scientists believe that the growth of black holes is intimately tied to the growth of galaxies themselves, with the energy and matter pulled into the black hole's accretion disk influencing the surrounding stars and gas clouds. In this sense, black holes might not just be cosmic oddities, they could be central players in the evolution of the universe. Looking even further into the future, black holes could become focal points for humanity's exploration of the stars. As our technology advances, it's not out of the realm of possibility that we could one day send missions to study the regions around black holes up close. While current space missions are limited to relatively close distances in our own solar system, future spacecraft could venture much further out into the galaxy, perhaps even to the black holes that lie at the heart of distant galaxies. Such missions could not only provide us with a deeper understanding of the ergosphere and other black hole phenomena, but they could also serve as stepping stones for humanity's expansion into the stars. Despite the many unanswered questions and immense challenges involved in studying black holes and their ergospheres, one thing is clear: the pursuit of knowledge in this field is one of the most exciting and potentially transformative scientific endeavors of our time. As we continue to push the boundaries of what we know, the mysteries of the ergosphere may unlock answers to some of the universe's deepest questions, and perhaps even reveal new ways for us to interact with the cosmos. The prospect of harnessing the immense power of black holes, particularly through energy extraction from the ergosphere, offers tantalizing possibilities for the future of space exploration and technology. One of the most exciting aspects of this potential lies in the application of the Penrose process, a theoretical mechanism that could allow us to tap into the energy of a rotating black hole. In the Penrose process, a particle splits into two, with one part falling into the black hole and the other escaping. The part that escapes carries away more energy than the particle initially had, meaning that energy is effectively extracted from the black hole's rotation. This idea has fascinated physicists for decades, but its practical application remains a distant dream. Despite the immense challenges in using this process in a real-world scenario, the idea of extracting energy from a black hole is too enticing to ignore, and it remains a subject of ongoing research. While energy extraction from the ergosphere remains a theoretical concept, it is not entirely without precedent in other fields of science. For example, harnessing energy from highly dynamic and extreme environments is not entirely new to us. Human ingenuity has already found ways to extract energy from natural processes on Earth, such as wind, tidal waves, and geothermal energy. The key difference with black holes, however, is that the forces at play are orders of magnitude stronger than anything we experience on Earth. If we could develop technology capable of surviving in such extreme environments, the potential for energy generation could be virtually limitless. Of course, the technological hurdles are immense. For one, the proximity required to extract energy from a black hole would place any spacecraft in a dangerous and unforgiving environment. The immense gravitational and radiation forces would quickly overwhelm most known materials, and ensuring the protection of any human or robotic mission would require innovative solutions. These solutions might include highly advanced shielding technologies or new materials designed to withstand the stresses of the ergosphere. The advancements necessary to achieve this would likely go beyond our current understanding of physics and materials science, potentially requiring breakthroughs in areas like nanotechnology or quantum engineering. But the challenges are not purely technological. There are also profound theoretical obstacles that must be addressed. For example, the Penrose process itself remains a subject of debate. While the mathematics behind it are sound, there is still uncertainty about whether such an energy extraction process could occur in the real world. Would it be possible to create conditions where particles can split in the way required for the Penrose process to work? Could the energy extracted from this process be enough to offset the immense energy costs of getting close enough to a black hole? These questions remain open, and answering them will require both further theoretical development and experimental validation. Moreover, we have to consider the broader implications of working with black holes. If we were to ever find a way to extract energy from a black hole, we would need to ensure that this process does not inadvertently destabilize the system. Black holes are not only powerful objects, they are also fragile in certain ways. Any disturbance in the delicate balance of matter and energy around a black hole could have unforeseen consequences. This means that while the ergosphere presents a potential goldmine of energy, it also represents a region of extreme danger. The potential for misuse or catastrophic failure could be catastrophic, and this risk would need to be carefully managed. Beyond the immediate technological and theoretical challenges, the study of the ergosphere could provide deep insights into some of the most profound mysteries of physics. One of these mysteries is the nature of angular momentum in black holes. Angular momentum is the measure of rotational motion, and it plays a central role in how rotating black holes interact with their environment. A black hole's angular momentum, combined with its mass, defines its structure and properties. Understanding how the ergosphere behaves, especially how it relates to the distribution of angular momentum in rotating black holes, could help us unlock new understanding of both general relativity and quantum mechanics. In addition to this, the study of black holes and the ergosphere could help address questions about the ultimate fate of information. One of the most paradoxical aspects of black holes is the so-called information paradox. According to quantum mechanics, information cannot be lost. Yet it seems that anything that falls into a black hole is lost forever, at least from our perspective. This raises profound questions about the fundamental nature of reality. Is it possible that the information that falls into black holes is somehow preserved, just not in a form that we can currently detect? Could the extreme conditions in the ergosphere, where space-time itself is twisted, provide clues about how information might be stored or recovered? These questions remain unanswered, and the study of the ergosphere offers a potential pathway to resolving them. The implications of all this are immense. If we can one day unravel the secrets of black holes, the ergosphere, and energy extraction from these cosmic behemoths, we could usher in an era of space exploration and technological advancement unlike anything humanity has ever seen. This could lead to practical advancements in space travel, energy production, and our understanding of the universe. Just as our understanding of the laws of physics revolutionized technology during the 20th century, so too could our study of black holes unlock new possibilities in the 21st century. However, even as we dream of these possibilities, we must remain grounded in the realities of our current technological limitations. It's important to remember that much of what we know about the ergosphere is still theoretical, and the actual study of black holes is still in its infancy. Even with advances in gravitational wave detection, our understanding of these phenomena is still developing. The next decade or so may see the development of new technologies that allow us to study black holes in greater detail, perhaps revealing more about the dynamics of the ergosphere and its potential for energy extraction. But these developments are likely to be gradual, requiring time, persistence, and innovative thinking. As we continue to explore the universe, the study of black holes will undoubtedly be a central focus. The ergosphere represents a region where space-time itself is stretched and twisted in ways that challenge our understanding of the laws of physics. It's a place where the very fabric of reality seems to bend under the weight of cosmic forces. For now, the mysteries of this region remain tantalizingly out of reach, but the pursuit of knowledge in this field will continue to inspire generations of scientists, engineers, and explorers to push the boundaries of what is possible. The ergosphere of rotating black holes is a region of space where the extreme forces of gravity, rotation, and energy converge in a way that challenges our understanding of the universe. It holds the potential to unlock new forms of energy, answer fundamental questions about physics, and provide new insights into the workings of the cosmos. While much of the research into black holes and the ergosphere remains theoretical, the possibilities are vast. With each new discovery, we come closer to unraveling the secrets of one of the most mysterious and powerful phenomena in the universe. And who knows? Perhaps one day, we'll be able to tap into the unimaginable energy contained within the ergosphere, changing the course of human history forever. As we continue to probe the mysteries of the ergosphere and black holes, it's worth considering the broader significance of these findings. The idea that black holes could serve as energy sources, or that their extreme conditions could help us unravel the fabric of spacetime itself, brings us closer to understanding the universe in ways previously thought impossible. But the journey to unlocking these secrets isn't just about technological advancements or extracting energy from a black hole. It's about fundamentally challenging our conception of reality. One of the key elements in studying black holes, and particularly their ergospheres, is the way in which these objects push the boundaries of our knowledge. A black hole isn't simply an object that pulls matter into a singularity. It's a place where our existing laws of physics break down, where time and space are no longer understood in the ways we're accustomed to. Black holes don't justify our understanding, they change the nature of what we think is possible in the universe. By continuing to study these enigmatic objects, we may find that some of our most deeply held beliefs about the universe need to be revised. In the process, we could find a new framework for understanding the nature of space, time, and energy that is beyond what we can currently imagine. The concept of extracting energy from a black hole is far from simple, but it's this very simplicity that makes the ergosphere so intriguing. The idea that rotating black holes might hold a vast energy reservoir, just waiting for us to unlock it, is a captivating one. While it's impossible to deny the immense challenges involved in such a task, the thought of tapping into such a powerful source of energy has the potential to revolutionize space exploration, energy production, and our understanding of the universe. Moreover, the study of the ergosphere could provide new insights into the interconnectedness of forces in the universe. Gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, all of these fundamental forces are involved in the behavior of black holes and their surroundings. By studying black holes in greater detail, especially their ergospheres, we might gain insights into how these forces work together, how they affect one another, and how they can be unified under a single, cohesive theory. But it's not just about energy extraction or unifying forces. There are other, more far-reaching consequences to studying the ergosphere. For instance, it could shed light on the mystery of dark matter and dark energy, two of the most elusive and poorly understood phenomena in the cosmos. While dark matter and dark energy are not directly related to black holes, understanding the behavior of spacetime around such extreme objects could give us new ways of thinking about these mysterious substances. If we can better understand the intricacies of spacetime in the ergosphere, we might be able to develop new techniques for studying the larger universe, including the strange behaviors of dark matter and dark energy. This could eventually help us answer questions that have remained unresolved for centuries. On a more practical level, the idea of harvesting energy from black holes could one day become a cornerstone of interstellar travel. The energy generated by rotating black holes could power spacecraft that venture far beyond the solar system, enabling us to explore distant stars, planets, and galaxies. This idea is still speculative, but it isn't entirely out of the realm of possibility. With the right technology, we could one day harness the power of a black hole's ergosphere to fuel missions that span light years. The idea of traveling to distant stars is another exciting avenue of exploration made possible by black holes. While traditional space propulsion methods are limited by the speeds achievable with current technology, black holes could offer us a new path to faster-than-light travel. The sheer energy contained within the ergosphere could theoretically allow us to bend spacetime in such a way that distances between distant points could be traversed in a fraction of the time it would take using conventional methods. While such technology may still be far off, the very possibility of interstellar travel opens up new frontiers for humanity, making the study of black holes and their ergospheres one of the most exciting fields of research in modern physics. But as with any great breakthrough in science and technology, the potential for misuse is always present. Harnessing the power of a black hole, no matter how theoretically possible, would require extraordinary precautions. The forces at play near a black hole are far beyond what we experience in everyday life, and even the slightest misstep could have catastrophic consequences. Any attempt to manipulate a black hole's energy would require rigorous safety protocols, as well as extensive monitoring and control to ensure that we don't inadvertently cause more harm than good. Furthermore, the potential consequences of extracting energy from a black hole could have far-reaching effects on the surrounding space-time fabric. Would the extraction of energy from a black hole cause it to lose its rotational momentum, or would it have other, unforeseen consequences on the black hole's structure? What would happen to the particles that fall into the black hole during the Penrose process? These questions highlight the complexity of dealing with such an extreme and powerful object. While the potential benefits of harnessing black hole energy are immense, the risks involved are just as high. The study of the ergosphere and black holes is about more than just energy extraction. It's about pushing the limits of human knowledge and exploring the deepest questions of the universe. The mysteries that black holes present are some of the most profound in science, and as we continue to probe these enigmatic objects, we will likely discover new truths about the very nature of reality itself. Whether it's gaining insights into the structure of space-time, understanding the nature of gravity, or developing new technologies that allow us to harness the power of these cosmic giants, the possibilities are limitless. The journey to understanding black holes, particularly the ergosphere, is a long one, and there is still much we don't know. But with each new discovery, we come closer to unlocking the secrets of the universe. And in doing so, we may find that the ergosphere, once an inscrutable region of extreme forces, could one day become a key to unlocking a future of limitless energy, space exploration, and perhaps even a deeper understanding of the cosmos. The exploration of black holes, particularly through the lens of the ergosphere, opens up an entirely new dimension of possibility, not just in theoretical physics, but also in how we might engage with the cosmos on a much grander scale. As we venture into this uncharted territory, it becomes clear that the ergosphere is not just a curiosity, it's a potential gateway to rewriting the very rules of how we interact with space, time, and energy. One of the more profound aspects of the ergosphere lies in its connection to the fabric of spacetime itself. In simple terms, the ergosphere is the region around a rotating black hole where spacetime is being dragged along with the black hole's rotation. This phenomenon is known as frame dragging, and it can be thought of as the fabric of the universe itself being stretched and twisted by the sheer force of the black hole's spin. To visualize this, imagine a large, heavy object sitting on a trampoline. As the object spins, it causes the surface to warp around it, creating a kind of vortex. This is similar to the way a rotating black hole warps spacetime. But unlike a trampoline, this warping affects everything, from light to matter, bending and twisting everything it comes into contact with. The implications of this stretching and warping of spacetime are both intriguing and, at times, mind-bending. The very act of a black hole spinning causes the space around it to behave in ways that are utterly foreign to our everyday experiences. In the ergosphere, objects and light cannot simply escape the black hole's influence in the usual manner. The concept of escaping becomes less about proximity and more about the relationship between space and motion. Objects within the ergosphere are forced to move in the direction of the black hole's spin due to this twisting of spacetime. To some degree, this means that escaping a black hole's pull, even from a region as close as the ergosphere, requires immense speed, faster than the speed of light for the most extreme cases. This is where the intriguing potential for energy extraction comes into play. The Penrose process, mentioned earlier, occurs when an object splits into two parts within the ergosphere. One part falls into the black hole, while the other escapes with a burst of energy. This energy is not only theoretically significant, it represents a practical mechanism that could, in the distant future, allow us to extract usable energy from the black hole itself. The fact that part of this energy comes from the black hole's rotational energy means that, in theory, a rotating black hole could be a limitless power source. But while the possibility of tapping into black hole energy is exciting, there are some significant hurdles that we must overcome. First and foremost is the technological challenge. Our current understanding of physics and technology is nowhere near advanced enough to attempt anything like the Penrose process. Even if we had the technology to reach a black hole and somehow harness its rotational energy, we would face an enormous array of obstacles. For one, we'd have to survive the extreme gravitational forces near a black hole. The closer we got to the event horizon, the more intense the tidal forces would be, stretching and compressing any object in ways that could easily tear it apart. It's not just a matter of energy extraction, it's about survival in an environment so extreme that the rules of physics themselves seem to change. Beyond the practical considerations, there are also ethical and philosophical implications to consider. If we were to develop the technology necessary to extract energy from a black hole, what would that mean for our place in the universe? The idea of harnessing the energy of a cosmic giant raises fundamental questions about how humanity relates to the cosmos as a whole. It may prompt us to reconsider our responsibilities when it comes to interacting with forces far beyond our control. Is it ethical to manipulate such powerful forces, or would such an endeavor lead to unintended consequences? And what if our actions were to disrupt the delicate balance of space-time, or even destabilize a black hole itself? These are questions we'll need to grapple with as we move closer to understanding and possibly interacting with black holes in a meaningful way. From a scientific standpoint, the study of the ergosphere doesn't just help us explore black holes, it provides insights into some of the most perplexing questions in physics. The nature of gravity, space-time, and the fundamental forces that govern the universe are all intricately connected to the behavior of black holes. As we continue to learn about the mechanics of the ergosphere, we uncover more about the way the universe operates on the most fundamental level. One of the biggest questions in modern physics is the unification of the forces of nature. Gravity, electromagnetism, and the strong and weak nuclear forces all operate in different realms, with different governing laws. Gravity, for instance, is described by Einstein's theory of general relativity, while the other forces are explained by quantum mechanics. Yet, despite their successes in their respective fields, these two theories do not mesh well when trying to describe extreme environments, such as the interior of a black hole. The ergosphere, where space-time itself is being twisted by the black hole's rotation, presents a natural laboratory for testing the limits of both theories. By studying black holes, particularly their ergospheres, we might one day find a way to reconcile general relativity and quantum mechanics, giving us a theory of everything, one that can explain both the largest structures in the universe, like galaxies and black holes, as well as the smallest, such as elementary particles. This is one of the ultimate goals of modern physics, and black holes, with their extreme conditions, are a key to understanding how these seemingly disparate forces can be unified. However, black holes do more than just challenge our understanding of physics. They also force us to confront the limits of human knowledge. As we attempt to peer into the heart of a black hole, we are confronted with the fact that some aspects of the universe may always remain beyond our reach. The singularity at the center of a black hole, for instance, is a point of infinite density and curvature, where the laws of physics as we know them break down completely. We may never be able to fully understand what happens at the core of a black hole, or even if we do, it may be so far removed from our experiences that it remains inconceivable. The ergosphere, with its strange properties and extreme conditions, forces us to reimagine our role in the universe. It challenges our basic assumptions about space, time, and energy, and pushes us to think beyond the confines of our everyday reality. By exploring these enigmatic regions around rotating black holes, we're not just uncovering the secrets of a distant corner of the cosmos. We're also uncovering new ways to understand the nature of reality itself. While we may still be far from practical applications such as extracting energy from black holes, The very idea that we can use their properties to enhance our understanding of the universe is a testament to the power of scientific curiosity. The ergosphere and the complex phenomena surrounding rotating black holes continue to be a focal point of research in astrophysics and general relativity, and as our tools and technologies advance, it's possible that we'll discover even more mind-bending aspects of these cosmic giants. The study of the ergosphere offers us a unique glimpse into a region of the universe where the usual rules no longer apply. It's a place where the very fabric of spacetime is warped and twisted by the power of rotation, creating new possibilities for understanding how the universe works. As we continue to explore these mysterious regions of space, we may find that black holes hold the keys to some of the deepest mysteries of existence, mysteries that, once unlocked, could forever change our perception of the cosmos. As we continue to explore the depths of the ergosphere and its potential, we must acknowledge the profound role it plays in our understanding of the universe. These cosmic entities challenge us to reconsider the nature of energy, space, and time, and perhaps, in the future, even push us towards new frontiers of technology and discovery. One fascinating aspect of the ergosphere is its ability to facilitate a theoretical concept known as the energy extraction from rotating black holes through the Penrose process. This process, proposed by physicist Roger Penrose in 1969, hinges on the unique properties of the ergosphere. In this region, the rotation of the black hole drags spacetime, allowing objects to gain energy when they split into two. One part of the object falls into the black hole, while the other escapes with more energy than the original object had before entering the ergosphere. The escaping object can carry this energy away from the black hole, essentially extracting rotational energy from the black hole itself. Theoretically, this process could serve as a source of energy, tapping into the rotational momentum of a black hole. At its core, the Penrose process is a remarkable and mind-bending concept because it defies our usual expectations of how energy is conserved in the universe. Normally, energy conservation dictates that energy cannot be created or destroyed, only transformed. The Penrose process, however, suggests that black holes, which are often considered the ultimate energy sinks, due to their immense gravity, can actually serve as sources of energy. This seems to break our conventional understanding of energy dynamics, yet the mathematics behind it checks out. The energy gained by the escaping particle is a result of the black hole's rotational energy being transferred during the process. While the Penrose process remains a theoretical concept, it has garnered significant attention in the scientific community. The possibility of harnessing energy from a black hole's rotation, even if it is currently beyond our technological capabilities, opens the door to a future where space exploration and energy consumption are fundamentally transformed. If we could one day create spacecraft capable of reaching the ergosphere, we might be able to tap into the immense energy of black holes, perhaps providing us with a virtually limitless power source. This could revolutionize space travel, enabling us to explore the farthest reaches of the universe, and even support energy needs here on Earth. But the challenges to this idea are substantial. First, reaching the ergosphere itself is no small feat. Black holes are located light years away from us, in some of the most hostile and distant regions of space. The nearest known black hole to Earth, known as the A0620-00 black hole, is over 3,000 light-years away. Even with our most advanced spacecraft, such as the Voyager probes, it would take tens of thousands of years to reach the vicinity of a black hole. Yet, as space technology continues to advance, the possibility of exploring such distant locations may become more feasible over time. Even if we could get close enough to interact with a black hole, the extreme gravitational forces at play in the ergosphere present another significant challenge. The region is known for its tidal forces, which can stretch and compress matter in extreme ways. Any object that ventures too close to a black hole will experience what is known as spaghettification, a phenomenon where the gravitational gradient is so intense that objects are stretched out into long, thin shapes. If we were to attempt energy extraction from the ergosphere, we would have to contend with these extreme tidal forces, which could tear apart any spacecraft or technology we send. In fact, no spacecraft we've designed today would survive such forces. This is why any attempt to harness energy from a black hole would require advancements in materials science and engineering far beyond what we currently have. Additionally, there's the question of how to actually capture and convert the energy extracted from a black hole. The energy gained from the Penrose process is carried away by a particle that escapes the black hole, but capturing and using that energy efficiently is a different challenge entirely. It would require advanced energy storage systems, perhaps even entirely new forms of technology, capable of absorbing and transmitting energy across vast distances. This presents an engineering challenge on an entirely new scale, one that would demand unprecedented innovation. While the practical applications of black hole energy extraction remain far off, the theoretical study of the ergosphere serves a deeper purpose. It allows us to explore the nature of space-time itself. The study of rotating black holes helps scientists probe some of the most fundamental questions in physics, especially those related to gravity, the structure of the universe, and even the unification of physics theories. Black holes, with their ability to warp space-time and create environments that challenge our understanding of physics, are like laboratories in the cosmos, giving us insights into the very building blocks of the universe. One particularly exciting aspect of ergosphere research is its potential to help bridge the gap between general relativity and quantum mechanics. General relativity, developed by Albert Einstein, describes the force of gravity and the behavior of spacetime on large scales, such as the motion of planets and galaxies. Quantum mechanics, on the other hand, governs the behavior of particles at the smallest scales. These two theories, while immensely successful in their respective domains, are fundamentally incompatible. General relativity does not incorporate quantum mechanics, and quantum mechanics does not incorporate the curvature of spacetime described by general relativity. The study of black holes, particularly rotating black holes and their ergospheres, offers a unique opportunity to explore the interplay between these two realms of physics. The extreme conditions found in the ergosphere, where spacetime is dragged and matter behaves in bizarre ways, could provide the key to understanding how these two theories might be unified. Some researchers believe that black holes could serve as testing grounds for a theory of quantum gravity, which would reconcile general relativity with quantum mechanics. If this theory were to emerge, it could revolutionize our understanding of the universe, potentially leading to new breakthroughs in physics and technology. Additionally, the study of rotating black holes and their ergospheres may reveal new insights into the behavior of the universe on the largest scales. The rotation of black holes could hold clues about the evolution of galaxies and the formation of structures in the cosmos. For example, some scientists believe that the rotation of supermassive black holes at the centers of galaxies plays a critical role in shaping the overall dynamics of the galaxy itself. The energy released by black holes, especially in the form of relativistic jets, can have a profound impact on the surrounding environment. Understanding the ergosphere and the forces at play in these regions could help scientists unlock the secrets of galaxy formation and the role black holes play in shaping the cosmos. The implications of this research are not limited to theoretical physics alone. Understanding the nature of black holes and their ergospheres could have practical applications in future space exploration. For example, advanced spacecraft could one day be designed to approach black holes, using their immense energy to power interstellar travel. The energy generated by a rotating black hole could provide the fuel needed for deep space missions, allowing humanity to venture farther into the universe than ever before. This type of energy source could be particularly valuable for missions to distant stars or for exploring the outer reaches of the solar system. The study of rotating black holes and their ergospheres, then, is not just a matter of theoretical curiosity. It's a key to understanding the fundamental workings of the universe. As our knowledge of these cosmic giants continues to expand, we may one day unlock new possibilities for energy, space travel, and even our understanding of the very fabric of reality itself. The ergosphere of a black hole represents a frontier of science, a place where the rules of physics break down, and where the mysteries of the universe await discovery. As we continue to explore the wonders and mysteries of the ergosphere, it becomes evident that the possibilities extend far beyond the theoretical realm. The study of black holes, especially their rotating counterparts, pushes the boundaries of our understanding, opening doors to new scientific concepts and even challenging the fundamental laws of physics. The ergosphere, as a region where space-time is twisted and distorted, is a place where the normal rules of energy, matter, and even time break down, creating a unique environment for researchers to explore and study. One of the most profound aspects of the ergosphere's influence is the potential to unlock a deeper understanding of the nature of time itself. In the ergosphere, space-time is not just curved, it is actively twisted by the rotation of the black hole. The effect of this twisting can alter the flow of time, causing it to behave in unexpected ways. Time dilation, a well-known effect of general relativity, becomes even more extreme in this region. Time, as experienced by an object within the ergosphere, is stretched to the point where the normal progression of seconds, minutes, and hours may appear drastically slowed down relative to an observer far outside the black hole's gravitational influence. This distortion of time is not just a curious quirk of the ergosphere. It has profound implications for our understanding of the relationship between space and time. Time dilation, when combined with the immense energy at play in this region, offers a tantalizing glimpse into the ways in which the fabric of the universe itself may be more flexible than we have previously imagined. Could it be that space-time is more malleable, more manipulable, than we thought? Could the twisting and warping of space-time in the ergosphere serve as a stepping stone to future technologies that allow us to manipulate time on a larger scale? While these questions remain unanswered, they highlight the importance of the ergosphere as a key area of study for future research in both theoretical and practical physics. Understanding how space-time behaves under such extreme conditions can inform not only our models of the cosmos but also potential applications for technologies that could harness the power of black holes. Another avenue of investigation involves the exploration of relativistic jets that are often emitted from the poles of black holes. These jets are composed of highly energetic particles that are propelled at nearly the speed of light, creating massive beams of radiation that extend for millions of light years. These jets are thought to be a direct consequence of the extreme gravitational forces at work in the ergosphere. The process by which these jets are launched is still not fully understood, but it is clear that the rotation of the black hole plays a critical role in their formation. What is particularly fascinating about these jets is that they carry enormous amounts of energy away from the black hole, potentially providing us with another method for harnessing black hole power. If we could find a way to tap into the energy contained in these jets, we might have access to vast reserves of power, far greater than anything currently available. The energetic particles in the jets travel at speeds close to the speed of light, and their energy could be harnessed for use in future technologies, such as advanced spacecraft propulsion systems or even energy generation for far-flung space stations. Yet again, the challenges are immense. The environment surrounding a black hole is extreme, with temperatures and radiation levels that are far beyond anything humanity has yet encountered. For any spacecraft or energy harvesting system to survive in this environment, it would need to be constructed using materials and technologies that can withstand unimaginable forces and radiation. Current materials science is nowhere near advanced enough to create structures that could survive such conditions, but as research into black holes continues, we may discover new materials or methods that make this type of energy extraction possible. Beyond the practical applications of black hole research, the study of the ergosphere also has profound implications for our understanding of the universe itself. Black holes, especially rotating ones, are not just isolated cosmic objects. They are central to the structure and evolution of galaxies. Supermassive black holes, which reside at the centers of many galaxies, have a powerful influence on their surrounding environment. The energy released by these black holes, whether through relativistic jets, accretion disks, or other processes, can shape the formation and behavior of stars, planets, and even the overall structure of the galaxy. In fact, some scientists believe that the rotation of a black hole plays a crucial role in the development of the galaxy itself. As black holes rotate, they create powerful magnetic fields that interact with the surrounding matter in the accretion disk. These interactions can help regulate the growth of the galaxy, influence the formation of stars, and even drive the dynamics of galaxy mergers. The ergosphere, as the region most directly influenced by the black hole's rotation, may be key to understanding how these processes unfold. One particularly intriguing aspect of this interaction between black holes and galaxies is the possibility that black holes could play a role in regulating the rate of star formation within their host galaxies. The energy emitted by black holes, particularly through their relativistic jets, could potentially inhibit the formation of new stars by heating up the surrounding gas and preventing it from collapsing into new stars. This mechanism, known as feedback, may help to explain the observed correlation between the size of a galaxy's central black hole and the overall properties of the galaxy, such as its star formation rate. Moreover, black holes may not only regulate star formation within galaxies, but they could also serve as a source of cosmic recycling. As matter falls into the black hole, it is not entirely destroyed. Instead, it is transformed into a highly energetic state. The energy and matter emitted from the black hole can influence the surrounding galactic environment, contributing to the creation of new stars, planets, and other celestial objects. In this way, black holes may act as cosmic engines, driving the ongoing cycle of creation and destruction that shapes the universe. While the ergosphere itself remains a place of intense interest for scientists, it also represents a reminder of the vast unknowns that still exist within the cosmos. Despite all that we have learned about black holes, space-time, and the mechanics of the universe, there is still so much we don't know. The study of black holes, particularly rotating black holes, presents one of the most significant frontiers in modern physics. It challenges our understanding of the fundamental laws of nature, pushes the limits of our technology, and forces us to reconsider the very nature of space, time, and energy. The mysteries of the ergosphere may one day lead us to new discoveries, new technologies, and new ways of understanding the universe. As scientists continue to probe the strange and enigmatic nature of black holes, we may find that the key to unlocking some of the deepest secrets of the cosmos lies within the twisting, distorted fabric of spacetime that surrounds these incredible objects. As we push forward with the exploration of the ergosphere and the broader phenomena surrounding rotating black holes, the implications of such studies stretch far beyond our current scientific frameworks. There are still many unresolved questions and mysteries, not only concerning the detailed mechanics of black holes themselves but also about the fundamental structure of spacetime in regions of extreme gravity. How does the intense warping of space and time near a black hole influence other regions of space? Are there other cosmic phenomena that share similar characteristics with the ergosphere, potentially expanding our understanding of the universe? To begin answering these questions, we must consider one of the most radical proposals arising from our study of rotating black holes: the possibility of energy extraction through the Penrose process. This idea, which originated from the work of physicist Roger Penrose, is one of the most fascinating and mind-bending concepts in modern physics. The Penrose process revolves around the nature of the ergosphere itself. As previously mentioned, the ergosphere is a region where spacetime is dragged and twisted by the rotation of the black hole, such that objects within this region cannot remain stationary. Any object in the ergosphere must move in the direction of the black hole's spin, or it will be torn apart by the extreme forces at play. However, within this region, there is a unique opportunity for energy extraction. The Penrose process involves splitting an object into two parts, one of which falls into the black hole, while the other escapes the ergosphere. The key insight is that the total energy of the system can be altered by this interaction. When one part of the object falls into the black hole, it has negative energy relative to an outside observer. As a result, the black hole's mass decreases, which leads to a corresponding increase in the energy available to the other part of the object, which escapes. This process essentially allows energy to be extracted from the black hole, using the rotating motion of the black hole itself. The implications of the Penrose process are enormous. In theory, if we could harness this method of energy extraction, it could provide an almost limitless source of power, drawn directly from the immense energy contained within the black hole. Imagine a spacecraft being able to orbit a black hole, using the Penrose process to generate energy and propel itself across vast distances in space. This could revolutionize our ability to explore the cosmos, providing a means of propulsion that doesn't rely on traditional fuel sources. Of course, There are numerous challenges to realizing this vision. For one, we would need to develop technology capable of surviving in the extreme environment surrounding a black hole. The radiation levels are extraordinarily high, and the forces at play could tear apart anything that comes too close. Furthermore, the precise mechanics of the Penrose process remain theoretical, and while it provides a tantalizing glimpse into the potential of black hole energy, much more research is needed to understand how we might begin to make it a practical reality. Even beyond the energy extraction possibilities, the study of rotating black holes and their ergospheres has implications for our understanding of the very nature of space and time. The idea that space-time can be twisted and contorted in such extreme ways suggests that there may be deeper, more fundamental forces at play in the universe than we currently understand. It raises the possibility that space-time, as we know it, may not be the rigid, fixed structure we once thought it was. Instead, it could be a dynamic, flexible entity that responds to the influence of massive objects, like black holes, in ways that we have yet to fully grasp. In addition to the Penrose process, researchers are also looking at other potential applications of the ergosphere's unique properties. One such area is the study of cosmic phenomena like gamma-ray bursts, some of the most energetic explosions in the universe. These bursts are thought to occur when massive stars collapse into black holes, releasing an enormous amount of energy in the form of gamma rays. The energy released during such events could be connected to the processes occurring in the ergosphere, as the intense gravitational forces of the black hole distort space-time and lead to the release of energy. Understanding the connection between the ergosphere and gamma-ray bursts could provide key insights into the nature of these extreme cosmic events. It might also offer clues about the origins of other mysterious cosmic phenomena, like quasars, pulsars, and the enigmatic dark matter that makes up a significant portion of the universe's mass. By studying black holes and the behavior of space-time in their vicinity, scientists may uncover new insights into the forces that govern the cosmos, from the smallest subatomic particles to the largest galactic structures. The ergosphere also plays a critical role in the formation of relativistic jets, another key feature of many black holes. These jets, which are composed of highly energetic particles traveling at nearly the speed of light, are thought to be generated by the intense magnetic fields created by the rotation of the black hole. The precise mechanics of how these jets form are still not fully understood, but it is believed that the energy and matter surrounding the black hole are funneled by the ergosphere into narrow, high-speed jets that shoot out along the black hole's rotational axis. These jets can have a profound impact on the surrounding galactic environment, influencing the formation of new stars, the evolution of galaxies, and even the behavior of supermassive black holes. Some scientists have proposed that these jets may be responsible for the formation of galaxy clusters, as the energy released by the jets could help to regulate the amount of matter that falls into the black hole, preventing it from overwhelming the surrounding space. As we continue to study the ergosphere, it is clear that the region around a rotating black hole is not just a place of destruction and chaos. It is a place of incredible complexity, where fundamental laws of physics are tested to their limits. The study of black holes, particularly their ergospheres, challenges our understanding of space, time, and energy, offering a glimpse into the most extreme and mysterious regions of the universe. Looking ahead, the exploration of rotating black holes may hold the key to unlocking some of the greatest mysteries of the cosmos. Whether it is through the study of relativistic jets, the potential for energy extraction, or the quest to understand the nature of space-time itself, the ergosphere provides a window into a universe that is far stranger and more complex than we could have ever imagined. While we are only just beginning to scratch the surface of what these objects can teach us, one thing is certain: the study of black holes and their ergospheres will continue to captivate and challenge scientists for generations to come. The exploration of black holes, particularly rotating black holes and their ergospheres, brings us closer to understanding some of the most fundamental forces and phenomena in the universe. As we dive deeper into the complexities of this subject, we encounter a wide array of implications, not just for theoretical physics but for our technological future and our understanding of reality itself. The ergosphere, in particular, challenges our preconceived notions about space, time, and energy. By continuing our exploration, We'll uncover how these concepts interlink in ways that push the boundaries of human knowledge. One of the most fascinating aspects of the ergosphere is the profound connection between rotation and energy. Black holes are often categorized into two types: rotating, Kerr, black holes, and non-rotating, Schwarzschild black holes. The defining characteristic of a rotating black hole is its angular momentum, a measure of how much the black hole spins. In a rotating black hole, the ergosphere exists outside of the event horizon, marking the region where spacetime is distorted so strongly that anything within it is forced to move in the direction of the black hole's spin. This warping of spacetime is not only a theoretical curiosity but a tangible phenomenon that can have significant impacts on both nearby objects and the energy dynamics of the surrounding area. In practical terms, the ergosphere represents a zone of intense gravitational and relativistic effects. As spacetime itself is dragged in the direction of the black hole's rotation, objects that venture too close cannot remain stationary. The velocity at which objects must travel simply to keep up with the rotating spacetime exceeds the speed of light in some instances. As a result, anything within the ergosphere is forced to move with the black hole's rotation. The result is a powerful interaction between matter and energy, as objects inside the ergosphere are subject to the extreme gravitational pull of the black hole. To understand how the ergosphere affects energy extraction, consider that any object that enters the ergosphere can, in theory, be used as a tool to siphon off energy. The concept of energy extraction comes from a broader understanding of how objects behave in the presence of a rotating black hole. As mentioned earlier, the Penrose process illustrates one such method where an object is split into two parts. One part falls into the black hole, contributing negative energy, while the other escapes with extra energy. This process exploits the rotational energy of the black hole and the fundamental laws of conservation of energy to provide a means of extracting usable power. In terms of practical applications, the notion of extracting energy from a black hole via the Penrose process opens up the possibility of using black holes as power sources. While this idea remains far from being realized, the theoretical framework suggests that if we can master energy extraction, it could provide a nearly unlimited energy source. This concept ties into the greater question of how we can use the extreme environments of space for practical benefit. Imagine harnessing the power of a black hole to propel a spacecraft or even provide energy for interstellar travel. While such scenarios might sound like the stuff of science fiction, the theoretical work that has gone into understanding black holes, especially rotating black holes, brings us one step closer to such a future. Another important phenomenon tied to the ergosphere is the creation of relativistic jets, which are some of the most powerful and energetic phenomena observed in the universe. These jets are thought to form when matter surrounding a rotating black hole is funneled into narrow beams by the black hole's immense gravitational and magnetic fields. These jets, traveling at relativistic speeds, close to the speed of light, are seen emanating from the poles of black holes, often extending across vast distances and carrying incredible amounts of energy. Relativistic jets are an important area of study because they provide clues about how black holes influence their surroundings. These jets are not just random occurrences but are part of the intricate interactions between the black hole's spin, its magnetic fields, and the surrounding matter. They can be thought of as a direct manifestation of the ergosphere's influence. The energy released in these jets can impact the formation of new stars, influence galactic dynamics, and contribute to the heating of the surrounding gas and galaxy clusters. The study of relativistic jets, therefore, is crucial for understanding not just black holes but the larger-scale processes that govern the evolution of galaxies. Moreover, the presence of relativistic jets has been linked to the phenomenon of active galactic nuclei (AGN), which are some of the brightest and most energetic regions in the universe. AGNs are typically powered by supermassive black holes at the center of galaxies, where the intense gravitational fields cause the surrounding gas and dust to spiral inward, forming a hot accretion disk. The energetic interactions within the ergosphere and the creation of relativistic jets play a critical role in the dynamics of AGNs, which are believed to be responsible for much of the energetic output of certain galaxies. The role of rotation in these processes cannot be overstated. The more rapidly a black hole spins, the stronger the ergosphere becomes, and the greater the potential for energy extraction and the generation of relativistic jets. This connection between rotation and power opens up new avenues for exploration, particularly in the context of understanding how supermassive black holes, which are thought to exist at the centers of many galaxies, contribute to the formation and evolution of their host galaxies. As we continue to examine the mysteries of black holes, we find that each new discovery raises more questions than it answers. The ergosphere, in particular, remains a source of fascination for scientists and astronomers. Not only does it challenge our understanding of spacetime and gravitational dynamics, but it also holds the potential to unlock some of the deepest secrets of the universe. The study of rotating black holes and their ergospheres also brings to light fundamental questions about the nature of spacetime itself. In regions where spacetime is stretched and twisted, the very fabric of reality seems to lose its usual properties. This brings up the question of whether there is an ultimate boundary to our understanding of physics, or if we can continue to push the limits of knowledge and uncover new aspects of the universe. The more we learn about rotating black holes, the more we realize how much we still have to discover. There may be phenomena beyond our current models of physics that are waiting to be uncovered. In the long run, the exploration of black holes, particularly the ergosphere, could lead to breakthroughs not only in theoretical physics but also in practical technologies. The very nature of spacetime itself is being challenged in these extreme environments, and our ability to understand and manipulate these forces could lead to new ways of thinking about energy, propulsion, and the future of space exploration. As we look to the future, the study of rotating black holes and their ergospheres is likely to remain one of the most exciting and dynamic fields of scientific inquiry. From the potential for energy extraction to the discovery of new cosmic phenomena, the mysteries surrounding black holes continue to captivate scientists and laypeople alike. Whether through theoretical research or the development of new technologies to study these enigmatic objects, the ergosphere remains a critical area of exploration in our quest to understand the deepest mysteries of the universe. The significance of the ergosphere extends beyond theoretical physics and energy extraction. As our understanding deepens, we begin to realize the potential implications this knowledge could have for practical applications, from space travel to energy generation, and even our broader understanding of the laws that govern the cosmos. In essence, the ergosphere exemplifies the strange and mind-bending phenomena that emerge when gravity, time, and space intermingle in the most extreme environments. Let's dive even deeper into the mechanics of how the ergosphere operates. The phenomenon is not just an interesting feature of black holes, but a fundamental part of their very nature. Space-time in the ergosphere is not simply curved in the way we might understand from everyday experiences. It's actively dragged in the direction of the black hole's spin. This warping creates the illusion that space itself is a fluid, swirling around the black hole, and it's this twisting of space-time that has such profound effects on anything nearby. In more technical terms, this effect is known as frame dragging. Frame dragging is a process predicted by Einstein's theory of general relativity, where the space-time around a massive rotating object is twisted as if it's being stirred by a spoon. The rotation of a black hole twists space-time so severely that everything within a certain radius is compelled to move with it. This effect is strongest at the event horizon, the boundary around a black hole beyond which nothing, not even light, can escape. But it extends outward into the ergosphere, the region just outside the event horizon. Objects within the ergosphere experience this intense dragging effect, and the energy needed to escape it is far greater than in the stable regions of space farther away from the black hole. However, this process opens the door to the Penrose process we discussed earlier. While objects inside the ergosphere can no longer remain stationary, they can still interact with the black hole in extraordinary ways. The key feature of the Penrose process is that it allows energy to be extracted from the black hole itself. Energy extraction via the Penrose process is fundamentally tied to the black hole's spin. The greater the angular momentum, or the faster the black hole rotates, the more pronounced the effects of frame dragging become, and the more energy can be harvested from the black hole. In essence, the more rapidly a black hole spins, the more accessible its rotational energy becomes. This is why rapidly spinning black holes are often of particular interest when studying potential energy extraction techniques. But what does this mean for the future of space exploration? While we're still far from building the technology necessary to harness black hole energy, the potential benefits are profound. If we could one day master the art of extracting energy from the ergosphere, the implications for space travel would be enormous. Imagine a spacecraft that can draw energy from a rotating black hole, providing an endless supply of fuel for interstellar journeys. Such a technology could make the long-distance travel of the future a reality, allowing humanity to explore the farthest reaches of the galaxy. The prospect of using black holes as power sources opens up an entirely new way of thinking about energy consumption in space, one where the immense power of cosmic objects is tapped into rather than feared or avoided. This kind of power could also have significant implications for energy production here on Earth. In theory, if we could develop a method of safely extracting energy from rotating black holes, perhaps through the controlled use of artificial objects or spacecraft that venture near enough to the ergosphere, it might offer a nearly limitless supply of clean energy. While this is still firmly in the realm of speculation, the idea that such exotic processes might one day be harnessed is tantalizing. Moving beyond energy generation, another area where the ergosphere could play a pivotal role is in the study of fundamental physics. The region around a black hole is a unique laboratory for testing the limits of general relativity. In the ergosphere, the effects of spacetime curvature are so extreme that they could provide insights into the nature of gravity, quantum mechanics, and even the fabric of spacetime itself. By studying how objects interact with the ergosphere, scientists could refine their understanding of the core principles of physics, and perhaps even reveal new laws that govern the universe. One of the key open questions in modern physics is the reconciliation of general relativity, which describes gravity at large scales, and quantum mechanics, which governs the behavior of particles at the smallest scales. The intense conditions found near rotating black holes, particularly in the ergosphere, offer an environment where these two realms collide. It is possible that the behavior of particles and energy in these regions could provide the clues needed to unify these two seemingly incompatible theories. Furthermore, the behavior of light near the ergosphere presents another area of intense research. Light, as it nears the black hole, undergoes a process called gravitational redshift, where its wavelength stretches out due to the strong gravitational field. The closer light gets to the event horizon, the more significant this effect becomes. In the ergosphere, light is still able to escape, but its wavelength is stretched so much that it can no longer be detected by normal telescopes. Studying these phenomena could provide a deeper understanding of how light behaves in extreme gravitational fields, and perhaps reveal new ways to observe and interpret the universe's most energetic phenomena. Moreover, the ergosphere could also contribute to the study of time itself. In this region, time behaves differently from what we experience in our daily lives. As space-time is dragged, clocks would appear to run slower the closer they are to the black hole, with time itself being stretched and warped in ways that defy our usual understanding. This could provide a unique opportunity to study the nature of time and whether it behaves consistently across all regions of space, or whether the universe's extreme environments allow for new forms of temporal behavior. In the realm of space exploration, the ergosphere may one day play an important role in the propulsion systems of advanced spacecraft. Although we're far from developing technology capable of safely navigating near a black hole, the concept of utilizing the ergosphere's energy could be the foundation for new propulsion methods. The immense gravitational forces at work could one day be leveraged for more efficient space travel, reducing the time and energy required to reach distant parts of the solar system, or even beyond. The future of space exploration could involve a series of missions aimed at understanding these mysterious regions more thoroughly, and perhaps one day exploiting their properties for human use. The ergosphere could also help solve some of the most profound mysteries of black holes themselves. For instance, the process by which matter is absorbed into a black hole is still not entirely understood. Theories suggest that once an object crosses the event horizon, it is lost to the black hole, never to be seen again. However, the region just outside the event horizon, where the ergosphere exists, is much less understood. If we can find ways to study objects in this region before they are irrevocably consumed by the black hole, we may be able to learn more about what happens inside the black hole, and perhaps gain new insights into the behavior of singularities and the nature of space-time. As we continue to explore the ergosphere and its implications, it's important to remember that these concepts are still at the cutting edge of theoretical physics. The extreme conditions near black holes challenge our understanding of the universe in ways that few other phenomena can. The exploration of rotating black holes, particularly their ergospheres, is not just about understanding these objects themselves but about pushing the boundaries of human knowledge and expanding our grasp of the cosmos. As research continues and technology advances, the ergosphere may one day reveal its secrets that could reshape our understanding of everything from energy production to the fundamental nature of space and time itself. As we continue to unravel the mysteries of the ergosphere, it's clear that the implications for our understanding of the universe stretch far beyond the confines of black holes alone. To truly grasp the potential of the ergosphere, we need to consider not just its theoretical implications but also the ways in which it could change the future of science and technology. One of the most intriguing aspects of the ergosphere is its potential to challenge our conventional notions of energy, power, and the very fabric of spacetime. For centuries, we have operated within the framework of classical physics, relying on models that describe the universe as a predictable, orderly system. However, black holes, and specifically the ergosphere, represent a departure from these predictable systems. They serve as a reminder that, in the most extreme environments, the rules we take for granted may break down or take on entirely new forms. The fact that energy can be extracted from the rotating mass of a black hole in the form of the Penrose process challenges our traditional ideas of energy conservation. The idea that energy can be pulled out of a black hole, an object traditionally thought to be an ultimate sink for energy, opens up new possibilities for the ways in which we think about the universe's fundamental forces. It suggests that energy isn't a one-way street. It can be manipulated, extracted, and even redistributed in ways that might have seemed impossible before. This notion of energy redistribution could eventually inform how we approach our energy crises here on Earth. In theory, the ability to harness energy from such an extreme source could fundamentally change how we generate power. Although we are still far from being able to extract energy from black holes, the discovery of such a process encourages innovation in energy technologies. It could inspire engineers to think about energy in entirely new ways, perhaps enabling more sustainable, efficient, and long-term solutions to power generation on Earth. While black holes are distant and inaccessible for the time being, the theoretical understanding of how energy can be extracted from these objects could form the basis for breakthroughs in energy production in ways we can't yet imagine. Beyond energy extraction, the study of black holes and the ergosphere has the potential to offer new insights into the very structure of space-time. General relativity, Einstein's theory of gravity, has been immensely successful at explaining the behavior of large-scale cosmic objects, but it still struggles when confronted with the quantum world. The intense conditions near the ergosphere could provide a unique environment for testing the boundaries of general relativity. The interaction between mass, gravity, and space-time in this region could offer clues about how to reconcile general relativity with quantum mechanics, a challenge that has stumped physicists for decades. The extreme environment of the ergosphere could also offer valuable data that may help resolve one of the greatest mysteries in modern physics: the nature of singularities. A singularity is a point in space where gravitational forces become infinite, and the laws of physics, as we know them, cease to apply. The center of a black hole, where the singularity lies, is one of the most mysterious regions of the universe. However, by studying the properties of the ergosphere and its relationship with the event horizon, scientists may be able to gain a better understanding of how matter behaves near these enigmatic points. This understanding could bring us closer to unraveling the true nature of black holes and the fundamental forces that govern the universe. Equally fascinating is the potential for studying the behavior of matter and the ergosphere itself. As objects approach the black hole's ergosphere, they begin to experience extreme forces. For example, objects in the ergosphere are subject to immense tidal forces that stretch and deform them. These forces could provide insight into the nature of gravity, allowing scientists to observe how matter responds to conditions of extreme curvature. By studying the material around black holes, we can learn more about the fundamental properties of matter and the forces that shape the universe at its most extreme. Moreover, the interaction of light near the ergosphere offers another avenue for study. As mentioned earlier, light near a black hole is subject to gravitational redshift, where its wavelength is stretched out, making it impossible to detect with traditional telescopes. However, by studying the effects of this redshift and the way light behaves in the ergosphere, scientists could develop new methods for observing distant cosmic events. This could lead to more advanced forms of telescopes and observational techniques, allowing us to explore regions of space that were once considered unreachable. Interestingly, these insights into the behavior of light near black holes might also be crucial in improving our understanding of the speed of light. Light's velocity is often considered to be a constant in our universe. However, in the context of the extreme conditions near a black hole, light behaves in ways that challenge this assumption. If we can understand how light interacts with the intense gravitational fields around a black hole, we may uncover new insights into the fundamental nature of light and its relationship to spacetime. This all ties into a broader philosophical implication. As we explore the ergosphere and other extreme environments in the universe, we may be forced to reconsider our most basic assumptions about reality. For centuries, humanity has believed that our understanding of the universe is complete, or at least close to it. However, the study of black holes, and the ergosphere in particular, reveals that there are still vast mysteries waiting to be uncovered. The fact that these regions defy many of our conventional ideas forces us to confront the limits of human knowledge and the potential for discovery. Moreover, the ergosphere and black holes challenge us to think about the nature of time itself. As we discussed earlier, time behaves differently near a black hole, slowing down and stretching as it nears the event horizon. The strange nature of time in the ergosphere calls into question our most fundamental assumptions about how time works. Could time be more malleable than we realize? Could the passage of time be fundamentally different in other regions of space, or even across different dimensions? These are questions that scientists are only beginning to explore, and they have profound implications for our understanding of the universe. From a more practical standpoint, the study of the ergosphere has the potential to unlock new methods for space travel. As we've mentioned, the energy that could theoretically be extracted from the ergosphere could serve as an incredibly powerful fuel source for spacecraft. The idea of using black holes as power stations may seem far-fetched today, but in the distant future, it could become a reality. Imagine the possibilities of interstellar travel powered by the immense energy of rotating black holes. It could make the exploration of other stars and galaxies a feasible endeavor, opening up the universe to human exploration in ways we've never dreamed possible. Another intriguing possibility is the potential for utilizing the ergosphere in the creation of artificial wormholes or other spacetime phenomena. Wormholes are theoretical structures in spacetime that act as shortcuts between two distant points in the universe. The extreme warping of spacetime around black holes may offer new insights into how wormholes could form, or how we might manipulate them for practical use. While this remains speculative, the study of black holes and their ergospheres could provide critical clues about the nature of spacetime and the possibility of faster-than-light travel. As we push further into the unknown, the exploration of black holes, particularly their ergospheres, promises to be one of the most exciting frontiers in modern science. Every step we take toward understanding these cosmic giants brings us closer to answering some of the universe's most profound questions. But it also raises new questions, some of which may challenge our very understanding of reality itself. As we continue to study the ergosphere, we are not just learning about black holes. We are learning about the nature of space, time, energy, and the fundamental laws that govern the cosmos. The ergosphere represents one of the most mysterious and tantalizing features of black holes. It's a region where spacetime is bent and twisted beyond our normal understanding, offering insights into the deepest corners of physics. Whether it's through energy extraction, understanding the behavior of light, or studying the fabric of spacetime itself, the ergosphere is a key to unlocking the universe's most profound secrets. And as our knowledge grows, Who knows what new revelations and breakthroughs await us on the horizon? As we continue to explore the implications of the ergosphere and its relationship with black holes, it's essential to revisit some of the fundamental concepts that lie at the heart of these cosmic phenomena. Black holes have fascinated scientists for decades, but their true potential as a source of knowledge and power has only begun to be realized in recent years. The ergosphere, as a region of spacetime in which space itself is twisted by the immense rotation of a black hole, represents a truly unique environment for scientific inquiry. At the core of the ergosphere lies one of the most perplexing and exciting features of black holes: the fact that space itself is dragged along with the black hole's rotation. This phenomenon, known as frame dragging, occurs because of the intense gravitational forces that are generated by a rotating black hole. The effect is most pronounced in the ergosphere, where the dragging of spacetime is so strong that nothing, not even light, can escape without being affected. This spaghettification of spacetime leads to a region where time itself behaves differently, further adding to the mystery surrounding black holes and the ergosphere. The concept of frame dragging was first predicted by Einstein's theory of general relativity, but it wasn't until the 1960s, when scientists began to study rotating black holes, that this phenomenon was fully understood. Frame dragging occurs because the rotation of a massive object causes the surrounding spacetime to twist. This is similar to how the rotation of the Earth affects the movement of objects near its surface, except in the case of a black hole, the effect is far more extreme and all-encompassing. As a result, any object or particle that comes too close to the ergosphere will find itself subject to this distortion, being dragged along by the black hole's spin. One of the most striking features of the ergosphere is its ability to allow for the possibility of energy extraction. The Penrose process, proposed by physicist Roger Penrose in 1969, is a theoretical method by which energy can be extracted from a rotating black hole. This process takes advantage of the fact that the ergosphere contains regions where objects can be split into two parts. One part falls into the black hole, while the other escapes, carrying away more energy than the object initially had. This process is one of the few known ways to extract energy from a black hole, and it holds great potential for the future of energy generation. The Penrose process works by exploiting the dynamics of objects within the ergosphere. Imagine a particle approaching the black hole, moving toward the event horizon. As the particle reaches the ergosphere, it splits into two smaller particles. One of these particles falls into the black hole, while the other escapes. The particle that escapes carries away more energy than the original particle, effectively stealing energy from the black hole. The energy that is extracted could theoretically be harnessed for practical use, providing a potential source of power far more efficient than anything currently available. Although the Penrose process remains a theoretical concept, it has captured the imagination of scientists and engineers alike. If it were possible to develop technology capable of extracting energy from the ergosphere, it could revolutionize the way we think about power generation. The energy that could be extracted from a black hole is virtually limitless, offering the potential to power entire civilizations for billions of years. However, the practical challenges of harnessing this energy are immense, and we are still a long way from being able to put this process into action. The idea of harnessing energy from a black hole raises a fascinating question about the potential future of space exploration. Could black holes become sources of power for spacecraft, enabling us to travel vast distances across the cosmos? If we could develop the technology to tap into the energy of a rotating black hole, it could make interstellar travel a reality. Imagine a spacecraft powered by the immense energy of a black hole, capable of reaching distant stars in a fraction of the time it would take using conventional propulsion methods. While this idea may seem like science fiction today, it is based on sound scientific principles, and advancements in space technology could bring it closer to reality in the future. As we look to the future, the study of black holes and the ergosphere could also lead to groundbreaking discoveries in the realm of theoretical physics. One of the biggest challenges facing physicists today is the reconciliation of general relativity, which governs the behavior of large-scale objects like black holes, with quantum mechanics, which describes the behavior of particles at the smallest scales. These two theories, while both incredibly successful in their respective domains, are fundamentally incompatible. The extreme conditions in the ergosphere could provide a unique environment for testing the limits of both theories, and perhaps even discovering a new framework that unifies them. The study of black holes and their associated phenomena has already led to significant advances in our understanding of the universe. For example, the recent discovery of gravitational waves, ripples in space-time caused by the collision of black holes, has provided new insights into the behavior of these cosmic objects. By observing the waves produced by black hole mergers, scientists have been able to test the predictions of general relativity in ways that were previously impossible. As we continue to study the ergosphere and its role in these extreme events, we may uncover even more surprising discoveries about the fundamental nature of space, time, and gravity. Another avenue of research that could be impacted by the study of black holes and the ergosphere is our understanding of the nature of singularities. Singularities, the points at the center of black holes where gravity becomes infinite and space-time breaks down, have long been a source of mystery for physicists. While our current theories of gravity and space-time break down at the singularity, the study of the ergosphere could provide valuable clues about what happens near these extreme points. By studying the behavior of matter and light in the ergosphere, scientists may be able to gain a better understanding of the conditions that lead to the formation of singularities and what happens to space-time at these points of infinite density. Additionally, the study of black holes and the ergosphere offers a new perspective on the nature of time itself. As we discussed earlier, the intense gravitational field near a black hole causes time to slow down relative to an observer further away. This effect, known as gravitational time dilation, becomes even more pronounced near the event horizon, where time essentially comes to a halt. The extreme nature of time near black holes challenges our understanding of how time works, and it could have profound implications for our understanding of the universe. Could time itself be more malleable than we think? Could there be ways to manipulate time in the same way that we manipulate space? These are questions that physicists are only beginning to explore, and the answers could lead to revolutionary advancements in our understanding of the universe. The study of black holes and the ergosphere, as extreme as they are, offers a window into the deepest mysteries of the cosmos. By continuing to explore these phenomena, we may be able to uncover secrets that could change the way we think about space, time, and energy. And as our knowledge grows, we may find that the universe is far stranger and more wondrous than we ever imagined. The ergosphere, then, is not just a curious feature of black holes, it's a key to unlocking the deepest secrets of the universe. As we continue to study it, we may find that the implications of its existence reach far beyond our current understanding of space-time. From energy extraction to the reconciliation of fundamental theories, the study of the ergosphere will likely play a crucial role in shaping the future of science and technology. As we delve deeper into the mysteries of the ergosphere, it's important to explore how this region of space-time behaves not just theoretically, but in the context of actual astrophysical phenomena. In particular, how does the ergosphere impact the dynamics of material around black holes? And what role does it play in shaping the overall structure of a black hole system? The presence of the ergosphere significantly alters the way objects behave in its vicinity. One of the most fascinating effects is the way particles and light interact with the strong gravitational forces near a rotating black hole. In the ergosphere, even objects that are not directly pulled into the black hole can experience substantial energy shifts, and sometimes even be accelerated to velocities approaching the speed of light. This is especially important for understanding the phenomena of relativistic jets, which are often observed around active black holes. These jets, composed of highly energetic particles, are launched from the poles of rotating black holes, and the ergosphere plays a central role in their formation. The dynamics of the ergosphere allow for the acceleration of particles to incredibly high speeds, sometimes reaching velocities close to that of light. This process is a result of the twisting of spacetime within the ergosphere, where particles are caught in the rotation and begin to spiral outwards, gaining more and more energy. The energy released in these jets can be immense, and understanding the mechanisms behind their formation is a crucial aspect of black hole astrophysics. One key observation in this area is that the jets are not emitted from within the event horizon of the black hole, but rather from the region surrounding it, specifically, the ergosphere. This distinction is important because it suggests that the material being ejected is not falling into the black hole, but rather is being expelled by the forces at play in the ergosphere. The exact mechanism behind this jet formation is still a topic of ongoing research, but it is widely accepted that the rotation of the black hole plays a significant role in the process. In addition to the production of relativistic jets, the ergosphere also influences the behavior of matter and accretion disks, the swirling clouds of gas and dust that surround many black holes. These accretion disks are thought to be a key source of the intense radiation observed near black holes, as the material in the disk is heated to extreme temperatures due to friction and gravitational forces. The interaction between the accretion disk and the ergosphere can lead to dramatic changes in the energy output of the system. One particularly interesting aspect of this interaction is the concept of magnetic fields in the region of the ergosphere. Magnetic fields play a central role in the behavior of accretion disks and relativistic jets, and the ergosphere's strong frame-dragging effects can significantly alter these fields. The rotation of the black hole, combined with the twisting of spacetime in the ergosphere, creates a situation in which magnetic fields are dragged along with the rotation. This phenomenon, known as the Blandford's-Najek process, is believed to be a mechanism through which black holes can emit energy in the form of powerful jets. This process works by transferring rotational energy from the black hole to the surrounding magnetic fields. The interaction between the rotating black hole and the magnetic field creates an energy flux that is emitted as a relativistic jet. The Blandford's-Najek process is a crucial piece in the puzzle of understanding how energy can be extracted from black holes and why certain systems produce such powerful jets. The ability of the ergosphere to twist and amplify these magnetic fields provides a significant boost to our understanding of these energetic phenomena. The more we learn about the ergosphere and its role in these processes, the more we realize how central it is to the dynamics of black hole systems. It's not just a passive region surrounding a black hole, it actively shapes the behavior of matter and energy in its vicinity. This interplay between the black hole's rotation, the ergosphere, and the surrounding material is key to understanding the full range of phenomena associated with black holes, from relativistic jets to the emissions of high-energy radiation. Another crucial area of study involves the potential for observing and detecting the ergosphere itself. Although the ergosphere is a region of spacetime, it's not a physical object that we can directly observe. Instead, we rely on indirect methods to study its effects on the material surrounding the black hole. One of the most promising tools for studying the ergosphere is the observation of X-ray emissions from accretion disks. As matter falls toward the black hole, it is heated to extreme temperatures, and in the process, it emits X-rays. By analyzing the X-ray spectrum from these regions, scientists can infer the properties of the black hole and its surrounding ergosphere. In addition to X-ray emissions, the study of gravitational waves provides another valuable tool for investigating the ergosphere. Gravitational waves are ripples in spacetime caused by the acceleration of massive objects, such as the collision of black holes. The merger of two black holes, in particular, can produce a signal that carries information about the black hole's spins, masses, and other characteristics. By studying these waves, scientists can learn more about the effects of the ergosphere and the black hole's rotation on the surrounding spacetime. In some cases, the behavior of the ergosphere may even influence the gravitational wave signature, providing a unique signature that could allow researchers to directly study its properties. The implications of these discoveries are profound, especially when it comes to our understanding of the broader structure of the universe. Black holes, and particularly rotating black holes with ergospheres, serve as natural laboratories for testing some of the most fundamental laws of physics. The extreme environments around black holes allow scientists to probe the limits of general relativity, quantum mechanics, and even the nature of time and space itself. One of the most exciting aspects of these studies is the potential to answer some of the deepest questions in science. For instance, black holes provide an opportunity to explore the nature of singularities, those regions of infinite density and curvature that exist at the centers of black holes. By studying the ergosphere and its interactions with matter and energy, we may gain new insights into the behavior of matter and space-time under extreme conditions. Could this be the key to understanding the true nature of singularities? And might it hold the answers to questions about the very fabric of reality? Furthermore, the study of ergospheres could also have implications for our understanding of the origin and evolution of the universe. Black holes are thought to play a crucial role in the formation of galaxies, stars, and other cosmic structures. By examining the role of rotating black holes in the context of their surrounding environment, we may uncover new clues about the mechanisms that drive the growth of cosmic objects and the evolution of the universe itself. In many ways, the ergosphere represents the frontier of black hole science. It is a region where the laws of physics are pushed to their limits, offering both challenges and opportunities for discovery. As we continue to explore the complexities of the ergosphere and its effects on the surrounding space-time, we are not just deepening our understanding of black holes, we are also expanding our comprehension of the universe as a whole. The more we study these extreme environments, the closer we come to unraveling the mysteries of space, time, and energy. Whether through the study of relativistic jets, accretion disks, or gravitational waves, the ergosphere is proving to be a central player in our quest to understand the universe's most enigmatic phenomena. And as technology continues to advance, so too will our ability to explore and comprehend the intricate workings of these cosmic giants. With every new discovery, we inch closer to understanding the true nature of black holes, the ergosphere, and their profound implications for the universe. The journey is far from over, and the mysteries of the black hole remain a captivating frontier in the realm of modern physics. As our tools and techniques improve, there is no telling what new revelations await us in the study of the ergosphere and the incredible forces that govern the behavior of the most powerful objects in the universe. As we continue to explore the ergosphere of black holes, we find ourselves not just dealing with theoretical concepts but with phenomena that could potentially lead to practical applications, transforming our understanding of energy production and space exploration. One of the most intriguing aspects of the ergosphere is its ability to facilitate energy extraction through a mechanism known as the Penrose process. This process, proposed by physicist Roger Penrose in 1969, takes advantage of the unique properties of the ergosphere to extract energy from a rotating black hole, turning it into a source of usable power. The Penrose process works by taking advantage of the fact that the ergosphere allows particles to have energy beyond the black hole's escape velocity. In simple terms, the energy available in the ergosphere is not bound by the same rules as in the rest of space, and particles can actually split into two components, one that falls into the black hole and another that escapes. The escaping particle carries away energy, and the particle falling into the black hole effectively has negative energy, reducing the black hole's mass. This seemingly paradoxical process has profound implications. First, it suggests that black holes, previously thought of as purely destructive objects, could in theory be used as sources of energy. The energy extracted could potentially be used for power generation in the distant future, perhaps in ways that we cannot yet fully comprehend. The sheer scale of energy that could theoretically be harnessed from a rotating black hole is staggering, opening up the possibility for technologies that could fundamentally alter how we think about energy production. However, while the Penrose process is theoretically possible, it remains largely speculative. The technology required to exploit such a process would be unimaginably advanced, and the energy needed to create the conditions for such an extraction is far beyond anything we currently have. But the very concept of extracting energy from the ergosphere speaks to the potential of black holes as resources, an idea that continues to inspire both scientists and futurists alike. What's fascinating about the Penrose process is not just the theoretical extraction of energy, but the potential implications it holds for our understanding of the very nature of black holes and the universe. The ability to remove energy from a black hole is not just a technical achievement, it's a fundamental change in how we perceive the life cycle of these cosmic giants. Instead of only growing larger by consuming matter, black holes could, in theory, shrink by losing mass through processes like the Penrose effect. In addition to the Penrose process, other ideas for energy extraction from black holes have been proposed, all of which involve interactions within the ergosphere. One such method involves the use of magnetic fields. Black holes, especially those with strong magnetic fields, have the potential to release vast amounts of energy by converting rotational energy into electromagnetic radiation. This process, known as the Blandford's-Nagic mechanism, works by using the black hole's rotation to power powerful jets of particles, which can carry away enormous amounts of energy. The Blandford's-Nagic process is fundamentally linked to the twisting of space-time within the ergosphere, which enables the acceleration of charged particles and the generation of high-energy electromagnetic fields. These jets, propelled by the energy of the black hole's rotation, can extend far beyond the black hole itself, carrying energy across vast distances. The potential to harness this energy, or even study it more deeply, could revolutionize our understanding of both astrophysics and energy production. But these theoretical energy extraction mechanisms, while exciting, come with challenges. Harnessing the energy of a black hole's ergosphere would require an unprecedented level of technology, precision, and understanding of the fundamental laws of physics. Current space exploration technologies are nowhere near capable of exploiting such energies, and the distances involved in reaching black holes, often located millions or billions of light-years away, make such endeavors seem distant, if not impossible. Yet, the fact that these processes can be modeled, studied, and understood gives us hope for future advancements. As our technology improves and as our understanding of black holes and their surroundings deepens, the concept of extracting energy from the ergosphere may one day shift from science fiction to reality. It remains a tantalizing possibility for future space missions, potentially providing humanity with a virtually limitless energy source in the far reaches of the universe. Beyond energy extraction, the ergosphere also holds important clues for the future of gravitational wave astronomy. Gravitational waves, ripples in spacetime caused by massive objects accelerating through space, have been a groundbreaking discovery in the field of astrophysics. The detection of these waves has already provided us with a wealth of information about the universe, particularly about the collisions and mergers of black holes. As we continue to study the ergosphere and its interactions with matter, we may discover new ways in which the ergosphere influences gravitational wave signals, providing an even deeper understanding of the behavior of black holes. The study of gravitational waves from black hole mergers is particularly relevant to understanding the ergosphere, as the interaction between merging black holes involves the extreme twisting of spacetime that characterizes the ergosphere. These events, when they occur, can send out waves across the universe, carrying with them vital information about the black holes involved. By studying these signals, we can learn more about the rotation, mass, and properties of black holes, as well as the nature of the ergosphere itself. Moreover, as gravitational wave observatories such as LIGO and Virgo continue to improve their sensitivity, we are likely to detect more mergers and black hole interactions. This will allow us to gather even more data on the nature of the ergosphere and refine our understanding of its role in black hole physics. The deeper we probe these phenomena, the closer we come to understanding not only the nature of black holes, but also the structure of spacetime itself. As we explore the ergosphere's influence on astrophysical phenomena, we must also consider its potential role in the search for life beyond Earth. While the idea of extracting energy from a black hole might seem far-fetched, the ergosphere could hold the key to understanding how energy might be harnessed in environments far from our home planet. In the future, as we search for habitable planets and develop the technology for interstellar travel, understanding the fundamental processes around black holes could provide insights into how life could exist in the most extreme environments of the universe. For instance, it is possible that life could exist on planets or moons that are orbiting stars near black holes, where the gravitational and energy dynamics created by the ergosphere could provide unique conditions for life to flourish. While this is purely speculative, the possibilities opened by our understanding of black holes and their surroundings suggest that we may one day look to the most extreme environments in space as potential sites for life. Furthermore, the study of black holes could offer clues about the fundamental nature of time, space, and the fabric of reality itself. The ergosphere, as a region where spacetime is stretched and twisted, offers a unique laboratory for testing theories of relativity and quantum mechanics. For instance, understanding how matter behaves in the ergosphere could help us uncover new laws of physics that govern the universe at its most extreme scales. As we continue to refine our understanding of the ergosphere and black holes in general, we find ourselves on the brink of discoveries that could transform our understanding of the cosmos. From energy extraction to gravitational waves, from the search for extraterrestrial life to the fundamental nature of SpaceTime, the study of the ergosphere is opening up new frontiers in our quest to understand the universe. The next few decades could see unprecedented breakthroughs in black hole research, and the ergosphere will undoubtedly be at the center of this scientific revolution. Whether we are looking for ways to harness energy from the most powerful objects in the universe, or using black holes to test the limits of our physical theories, the ergosphere remains one of the most exciting and mysterious regions of space. As we continue our journey through the enigmatic world of the ergosphere, we must consider the even broader implications this region holds for our understanding of the very fabric of the universe. The ergosphere, as part of a rotating black hole, is a profound manifestation of the interplay between matter, energy, and spacetime itself. The twisting of spacetime near the event horizon of a rotating black hole creates a zone where the laws of physics, as we currently understand them, appear to bend in extraordinary ways. This warping isn't just an abstract concept but a real, measurable phenomenon that we can explore through advanced astrophysics and cosmology. One of the most crucial areas in the study of rotating black holes is understanding the relationship between the ergosphere and the event horizon, the boundary beyond which nothing, no matter or light, can escape the black hole's immense gravitational pull. In non-rotating black holes, the event horizon marks the point of no return. Once anything crosses it, there's no going back. However, in rotating black holes, the ergosphere extends outside the event horizon, and this introduces a new layer of complexity to the black hole's dynamics. Inside the ergosphere, spacetime itself is in motion, carried along by the black hole's rotation. This motion creates what is known as frame dragging, a phenomenon where the rotation of the black hole essentially drags the fabric of spacetime along with it. This effect is most intense near the event horizon, where spacetime is twisted to its extreme. Frame dragging has profound implications for both the behavior of matter within the ergosphere and the energy interactions that can occur there. For example, any object that enters the ergosphere is forced to co-rotate with the black hole to some extent. The closer it gets to the event horizon, the more it is affected by this dragging effect. The object cannot remain stationary relative to a distant observer. It must move in the direction of the black hole's rotation. This interaction is a consequence of the conservation of angular momentum and the geometry of spacetime in this region. However, it's also what opens the door to energy extraction methods like the Penrose process. The spinning black hole provides an environment where the laws of physics can be manipulated to allow energy to be extracted and potentially harvested. This also leads to the potential creation of energetic jets of particles and radiation, phenomena that have been observed emanating from some black holes. These jets, while not directly caused by the ergosphere, are thought to be strongly influenced by the immense rotational energy that black holes possess. The angular momentum of a black hole can lead to the acceleration of charged particles along magnetic field lines, creating jets that shoot out from the black hole's poles at nearly the speed of light. These jets can carry away significant amounts of energy, and understanding how this happens could provide key insights into both astrophysics and high-energy particle physics. One of the most fascinating aspects of the ergosphere and its interactions with the rest of the universe is its potential role in the formation of some of the most energetic and mysterious phenomena in the cosmos. For instance, it is believed that supermassive black holes at the centers of galaxies may drive the formation of active galactic nuclei, AGN, powerful sources of radiation and particle emission that can outshine entire galaxies. The energy and matter ejected from the ergosphere could be instrumental in the creation and sustenance of these AGN, which are among the brightest objects in the universe. The processes happening within the ergosphere thus play a crucial role in the energy dynamics of the universe on a grand scale. But the ergosphere is not just a place where energy can be extracted, it is also a place where the very nature of time and space begins to behave in unfamiliar ways. Time dilation, an effect predicted by Einstein's theory of relativity, becomes extremely pronounced near the ergosphere. As an object approaches the event horizon, time for it would appear to slow down relative to an outside observer. This means that, from the perspective of someone far away from the black hole, events within the ergosphere unfold at a slower pace. This effect is a consequence of the strong gravitational field and the warping of spacetime, and it serves as a stark reminder of how deeply gravity influences the nature of time itself. The phenomenon of time dilation near rotating black holes has fascinating implications for both theoretical physics and practical considerations in space exploration. If we could ever travel near a black hole, without crossing the event horizon, of course, the effects of time dilation would mean that time for us would pass differently compared to those far from the black hole. This could create interesting opportunities for long-term space travel, where travelers near the black hole would experience much less passage of time compared to people far away. While this idea is far from being practically achievable, it highlights the mind-bending nature of black holes and the exotic environments they create. The ergosphere's effects on time and space could also help us understand how the universe itself came to be, offering insight into the very early moments following the Big Bang. Early in the history of the universe, space itself was expanding, and the forces that shaped it were influenced by extreme gravitational effects, much like those seen near black holes today. Studying the ergosphere could give us a better understanding of how spacetime behaves under extreme conditions, and how these conditions might have contributed to the formation of the universe's large-scale structure. It might even provide clues about how the early universe's energy was distributed and how the massive cosmic structures we see today came into being. As we look further into the future of black hole research and the study of the ergosphere, there are several important technological and scientific advancements on the horizon. Gravitational wave astronomy, for example, will continue to improve our understanding of the interactions between black holes and the ways in which their ergospheres affect the surrounding spacetime. As we detect more gravitational waves from the mergers of black holes, we will gain a clearer picture of how these cosmic events unfold, and how the ergosphere influences the dynamics of the merging black holes. Moreover, advancements in high-energy astrophysics and particle physics could eventually allow us to probe the regions surrounding black holes in greater detail. Instruments capable of detecting the high-energy radiation emitted by black holes could provide new insights into the nature of the ergosphere and the ways in which matter and energy interact in this extreme environment. As our understanding of quantum gravity deepens, we may also uncover new phenomena that emerge in the ergosphere, potentially leading to breakthroughs in our understanding of quantum mechanics, spacetime, and the very nature of reality. Ultimately, the study of the ergosphere is not just an academic exercise but a window into the fundamental workings of the universe. By investigating the ways in which spacetime behaves around rotating black holes, we are exploring the nature of gravity, energy, and matter on the largest and most extreme scales. These investigations may one day lead to practical applications, such as energy extraction, new propulsion technologies for space travel, or even deeper insights into the unification of the fundamental forces of nature. However, we are still far from fully understanding the complexities of the ergosphere, and much work remains to be done. The very existence of the ergosphere, along with the processes that occur within it, challenges our current understanding of physics and pushes the boundaries of what we thought possible. The mysteries that remain to be unraveled in this region of space are tantalizing and may hold the keys to some of the most profound questions about the universe. The exploration of the ergosphere, and of black holes in general, continues to be one of the most exciting frontiers in modern science. As our knowledge grows and our technologies improve, we are likely to make new discoveries that will reshape our understanding of the cosmos. From energy extraction to time travel, from the formation of galaxies to the fundamental nature of reality, the ergosphere stands as one of the most fascinating and mysterious regions of space. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.